The concept of dark energy emerged in the 1990s when astronomers studying Type 1a supernovas discovered something unexpected. Not only was the universe expanding, but it was accelerating as well. This came as a surprise because, according to the laws of gravity, the expansion of the universe should be slowing down due to the pull of matter. The discovery hinted at the existence of some mysterious form of energy, one that could push things apart instead of pulling them together. This is where dark energy enters the picture. Today, scientists believe dark energy accounts for about 70% of the total energy in the universe. But what exactly is it? Unlike ordinary matter, dark energy isn't a tangible substance. Instead, it's a kind of force with negative pressure that counteracts gravity, causing the universe's expansion to speed up. From the perspective of general relativity, this means dark energy bends space-time in a way that accelerates cosmic growth. To describe its effects mathematically, scientists use an extra term in Einstein's equations, called the cosmological constant, represented by the Greek letter lambda. The cosmological constant is simple in concept. It's a constant energy density that doesn't change over time. However, it brings up a major issue. According to particle physics, the energy of the quantum vacuum should be 120 times greater than what cosmology suggests for the cosmological constant. This discrepancy, known as the cosmological constant problem, is one of the biggest mismatches between theory and observation in modern science. To solve it, some researchers suggest extreme fine-tuning, or they speculate that there might be unknown mechanisms that cancel out the effects. Because of this problem, scientists have considered alternative models. One such alternative is quintessence, a dynamic field that changes over time and whose energy density varies as the universe evolves. Unlike the cosmological constant, quintessence could fluctuate, offering a more complex and flexible explanation for cosmic acceleration. However, current data doesn't yet require such a complex explanation, so it remains an area of active research. Other models suggest that dark energy might not be a form of energy at all. Instead, it could be the laws of gravity themselves that need revision. For example, theories like ferrogravity, which adjust the curvature term in Einstein's equations, propose changes in gravitational forces on large scales. There are even models inspired by string theory, which suggest that extra dimensions or brane effects could be responsible for the accelerated expansion. To test these theories, astronomers rely heavily on observations, mapping the cosmic microwave background, studying galaxy distributions, and measuring the effects of weak gravitational lensing provide critical clues. For instance, looking at how galaxies cluster together or the patterns of baryon acoustic oscillations, the sound waves in the early universe help scientists fine-tune their models. So far, the simplest explanation, a constant cosmological constant, still fits the data best. However, upcoming missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope are designed to push these measurements to new levels of precision. These missions will look for signs that dark energy's density might change over time, which could help differentiate between the cosmological constant and quintessence. They'll also search for subtle shifts in the geometry of the universe and the way structures like galaxies grow, which could shed light on alternative gravity models. This growing body of data could help refine our understanding of the universe's expansion, providing deeper insights into dark energy's true nature. A fascinating aspect of dark energy is that it didn't always dominate the universe. For most of cosmic history, dark matter and ordinary matter played the key roles in the expansion. Only when the density of matter dropped enough did dark energy take over, accelerating the expansion. This shift is a pivotal moment in the history of the cosmos and holds crucial clues to how structures in the universe formed. Dark energy's influence only becomes noticeable on the grandest cosmic scales. It's a property of space itself. This behavior doesn't align with our usual understanding of how things work. It's almost as if the vacuum of space has its own unique set of rules. This mysterious force continues to baffle scientists as dark energy is invisible, undetectable, and leaves no trace in our local surroundings. Yet, it's the key player in driving the future expansion of the universe. Until we can fully grasp its nature, our understanding of cosmology will remain incomplete. The universe is speeding up its expansion, but why? The answer remains just out of reach. So, What about dark matter? The idea of dark matter was first proposed in the 1930s by Fritz Zwicky. He noticed that the visible mass in galaxy clusters didn't explain the high velocities of the galaxies within them. Later, astronomers studying the rotation of galaxies discovered a similar problem. Stars far from the center of galaxies were moving faster than expected, even though the density of visible matter was low. This suggested the presence of unseen mass surrounding these galaxies, forming halos that kept the galaxies gravitationally bound. Since then, dark matter has become a crucial component in cosmological models. Unlike ordinary matter, which interacts with light and other forces, dark matter only interacts through gravity. This means we can't observe dark matter directly, but we can measure its effects on the dynamics of galaxies and other cosmic structures. It seems to be spread out in large quantities around galaxies, galaxy clusters, and even in the early universe. Dark matter influences everything from the formation of galaxies to how cosmic radiation spreads. Various pieces of evidence from different areas of astronomy support its existence, making it a key part of modern cosmology. There are several theories about what dark matter is made of. The most common candidate is WIMPs, weakly interacting massive particles. These particles would have mass and interact through forces other than gravity, such as the weak nuclear force, but very rarely. Scientists are trying to detect these particles using underground experiments, such as the Xenon 1T detector, which looks for collisions between WIMPs and atomic nuclei. However, so far no direct evidence has been found, though the search continues with increasingly sensitive technologies. Another possibility is axions, extremely light particles predicted by certain theories about the strong nuclear force. Axions could convert into photons in the presence of magnetic fields, which makes them detectable through specialized experiments like the ADMX. These experiments search for specific frequencies that correspond to different particle masses. There are even proposals for ultralight axions, which could have an impact on how small-scale cosmic structures form. Some researchers think dark matter might interact with itself, meaning its particles could collide with each other without involving ordinary matter. This idea could help explain some inconsistencies seen in galaxy centers, where density distributions don't match theoretical predictions. Simulations that include self-interacting dark matter produce density profiles that more closely match what we observe in the universe. Gravitational lensing, where light from distant galaxies is bent by the gravity of objects in front of them, provides another way to map dark matter. The weak lensing effect, in particular, helps scientists visualize the distribution of dark matter in the universe. These maps show that galaxies and other visible structures follow an invisible web of dark matter, accumulating in the areas where the dark matter density is higher. When compared to simulations, these observations support the idea of the LTZDM model, which suggests that dark matter is cold and moves slowly compared to the speed of light. This model also helps explain how galaxies and clusters formed in the early universe, as seen in deep field observations. The Cosmic Microwave Background (CMB), which measures the leftover radiation from the Big Bang, also points to dark matter's role. Detailed measurements by missions like WMAP and Planck have shown that dark matter is necessary to explain the density fluctuations in the early universe. These fluctuations are reflected in the CMB's acoustic peaks, which give us insight into the distribution of matter in the early cosmos. Observations support the idea that the universe is made up of about 25% dark matter and 5% ordinary baryonic matter. The idea that primordial black holes could be responsible for dark matter has also resurfaced, especially following the detection of gravitational waves by LIGO. These black holes could have formed in the early universe and survived to this day. However, recent observations from microlensing and the cosmic background radiation suggest that primordial black holes can't account for all dark matter. While they might contribute a small fraction, they aren't the main source of dark matter. Alternative gravity theories are another avenue of exploration. Some theories propose modifications to Newton's and Einstein's laws, especially at larger cosmic scales. One such theory, known as modified Newtonian dynamics, MOND, adjusts gravitational acceleration in low-density regions to explain the behavior of galaxy rotation curves without needing dark matter. However, these theories fail to match observations of the cosmic background and large-scale structures, which further supports the hypothesis that dark matter is a real physical entity. Current experiments, such as those at the Large Hadron Collider (LHC), are also searching for indirect signs of dark matter. The idea is that dark matter particles might decay into other detectable particles, leaving behind missing energy. So far, no clear evidence has been found, but new experiments continue to push the boundaries of what's possible, testing higher energies and looking for new types of decay. The search is expanding to include new particles beyond the standard model of physics. The quest for answers now includes studying ultra-diffuse galaxies and anomalous satellite galaxies. Some of these galaxies contain little or no dark matter, which challenges current expectations. On the other hand, some galaxies seem to be composed almost entirely of dark matter. These extremes offer a unique opportunity to test theories about how dark matter interacts with ordinary matter and could help resolve some of the remaining mysteries. Dark matter continues to be an essential piece of the puzzle when it comes to explaining the universe's evolution across all known scales. Although we haven't yet fully figured out what it is, its effects on cosmic dynamics and structure are undeniable. New technologies like the Vera Rubin Observatory, along with upcoming space missions, promise to give us even more precise data. These advancements will enable us to rigorously test current models, and may even provide the first direct evidence of dark matter's existence. So what is the theory of quantum gravity? General relativity works perfectly well on large scales, like planets, stars, and galaxies, but quantum mechanics dominates the tiny world of particles. Both theories are highly successful in their respective domains, yet they contradict each other when we try to apply them to extreme conditions, like inside black holes or during the early moments of the universe. General relativity treats space-time as a smooth, continuous fabric, while quantum mechanics requires that everything be quantized, broken into discrete units. The challenge is uniting these two perspectives into a single theory, quantum gravity. The problem becomes especially tricky when we try to apply quantum mechanics to strong gravitational fields, where the effects of gravity are so intense that quantum behavior can't be ignored. When we try to treat gravity as just another force in quantum theory, we run into mathematical issues. The equations become non-renormalizable, meaning they produce infinite values that can't be dealt with. This makes it impossible to build a traditional quantum theory of gravity. One of the most explored ideas to solve this is string theory. Instead of imagining particles as tiny points, string theory suggests that the fundamental building blocks of the universe are tiny, one-dimensional strings. These strings vibrate in different patterns, each corresponding to a different particle. One of these vibrations is associated with the graviton, the theoretical quantum particle that mediates gravity. This allows gravity to fit into the quantum framework. But for string theory to work, it needs extra dimensions more than the 4-3 of space and 1 of time that we experience. In its simplest form, string theory requires 10 dimensions, with 6 of them being compactified at the subatomic level. These additional dimensions influence the properties of particles in our universe, opening up a whole new realm of possibilities for unifying the fundamental forces. However, the vast number of potential solutions to the equations makes it hard to know which model is the right one. Another approach is loop quantum gravity, which takes a different route. This theory tries to directly quantize space-time itself. In this view, space isn't continuous but is made up of a network of loops that define minimum areas and volumes, kind of like the way energy levels in atoms are quantized. Time also behaves differently in this theory. It emerges from the interactions of the network rather than being an independent backdrop. Unlike string theory, loop quantum gravity doesn't require extra dimensions and is based on well-established mathematical principles. It also offers some intriguing ideas, like the possibility that the universe existed before the Big Bang and that it emerged from a quantum bounce. It also makes testable predictions, such as modifications to the radiation emitted by black holes known as Hawking radiation. However, it still doesn't fully account for matter or non-gravitational forces, which limits its scope for now. There are also other theories, such as causal dynamical triangulations, which builds spacetime by summing up different possible geometric configurations. And then there's emergent gravity, which suggests that gravity isn't a fundamental force but rather a statistical phenomenon. In this view, gravity would emerge from the collective behavior of microscopic particles, much like temperature arises from the motion of atoms. These ideas challenge the traditional notion of spacetime and aim to provide a new way to think about gravity. The major challenge for all these theories is the lack of experimental evidence. Quantum gravitational effects only become noticeable at incredibly high energy scales, far beyond the reach of today's particle accelerators. This means that while the theories are fascinating, they remain largely speculative, with no way yet to directly test their predictions. One area where we might find some clues is in cosmology. For instance, primordial gravitational waves, which are tiny ripples in spacetime caused by quantum fluctuations during cosmic inflation, could provide a way to indirectly probe quantum gravity. Detecting these waves would offer a window into the physics of the Planck scale, where quantum gravity effects are expected to become significant. Another potential source of insight is the study of black holes. The concept of Hawking radiation, which suggests that black holes can slowly lose mass over time, requires a quantum description of gravity. Understanding this process, especially how information is lost or preserved in a black hole's interior, is key to developing a complete theory of quantum gravity. Proposals like the firewall hypothesis and ideas about the reconstruction of black hole interiors are directly tied to these questions, making black holes natural laboratories for testing quantum gravity. Ultimately, the unification of quantum mechanics and gravity isn't just a technical problem, it's a profound shift in how we understand the universe. It may require us to rethink fundamental concepts like the nature of space and time, or even how we understand causality. As of now, quantum gravity remains a work in progress, with many different approaches competing for attention. The road ahead will require both fresh theoretical insights and new experimental techniques. While no single theory has emerged as the definitive answer yet, each approach is helping to clarify the limitations of the existing models, guiding us toward a deeper understanding of the universe. As new evidence continues to emerge, we'll eventually be able to narrow down the competing models. Until then, quantum gravity remains one of the deepest and most challenging frontiers in theoretical physics. What about the potential inconsistency in expansion measurements? The Hubble constant defines the current rate at which the universe is expanding. It can be measured using two primary methods, by observing nearby supernovae and galaxies, or by analyzing the cosmic microwave background, CMB. Local universe measurements suggest a value of about 73 kilometers per cm per megaparsec. But when looking at the early universe, particularly through data from the Planck satellite's CMB analysis, a lower value of approximately 67 kilometers per cm per megaparsec is found. This ongoing discrepancy is known as the Hubble tension. The local measurements are based on a method called the cosmic distance ladder, which starts with set-fied variables and supernovae as standard candles. These methods rely on precise calibration, taking into account things like dust and host galaxy properties. Even with improvements in techniques, different research teams consistently find similar high values. On the other hand, the CMB-based values rely on fitting the LFEED-CDM model, the standard model of cosmology, to the early universe, and then extrapolating to infer the current rate of expansion. Both methods are statistically sound and internally consistent, yet the results they provide remain incompatible. The discrepancy has grown more significant as measurement precision has improved, reaching levels beyond 5 sigma in some cases. This raises the possibility that the tension could point to new physics beyond what the current models explain. One explanation is that the early universe might have behaved differently. For example, introducing additional relativistic particles, sometimes called dark radiation, could shift the inferred Hubble constant from CMB data without affecting local measurements. Some theories propose the existence of early dark energy, an energy component that briefly influenced the universe before light decoupled during recombination. These adjustments would change the universe's expansion rate in its early stages. Alternatively, some theories focus on modifications to late-time physics, such as changes in the dynamics of dark energy or interactions between dark matter and other components. These models would accelerate the recent expansion rate, aligning it with the higher values observed in local measurements. However, adjusting late-time physics risks conflicting with other observations, such as the formation of cosmic structures or baryon acoustic oscillations. Ensuring consistency across all datasets remains a significant challenge. Others consider the possibility of unknown systematics affecting one or both measurement methods. Critics of the distance ladder argue that uncertainties in Cepheid calibrations or sample selection could introduce errors. Meanwhile, assumptions in the CMB-based models, like the universality of the del-CDM model, might also skew the results. To address these concerns, independent surveys and calibration techniques are essential. New methods like gravitational wave standard sirens, using the waves emitted by merging black holes or neutron stars, could offer promising alternatives. Another idea that's been proposed is the possibility of a large-scale inhomogeneity in the universe, such as residing in a cosmic void. If we were located in a large underdense region, this could affect local expansion measurements. However, this would challenge the cosmological principle, which assumes the universe is homogeneous on large scales. Observations of the large-scale structure do not support such a deviation. So while this idea remains theoretically interesting, it's still constrained by the available data. Future missions will be pivotal in resolving these questions. The James Webb Space Telescope (JWST) and the Vera Rubin Observatory will refine local measurements with higher precision, while missions like Euclid and the Roman Space Telescope will probe the large-scale structure and the universe's early evolution. By combining these new datasets, we'll be able to test the consistency of cosmological models more rigorously. These observations could either resolve the Hubble tension or provide more evidence that new physics is required. The tension also affects other parameters, such as the matter fluctuation amplitude, sigma 8, which shows slight discrepancies between early and late universe measurements. This raises additional questions about how cosmic structures grew. If both the Hubble tension and the matter fluctuation discrepancies persist, they may point to interlinked physical effects, potentially offering important insights into dark energy and neutrinos. As measurement precision continues to improve, cosmologists will need to explore broader theoretical frameworks. This includes non-standard inflation models, modified gravity theories, and evolving dark sectors. These theories must be able to align with all available observational data. A unified explanation for the Hubble tension would have profound implications for our understanding of the universe's fundamental workings. Whether the Hubble tension points to new physics or is simply the result of systematic errors remains an open question. However, its persistence across multiple datasets suggests it's an issue that requires serious attention. The tension has become one of the most intriguing challenges in modern cosmology, highlighting the delicate interplay between observation, theory, and interpretation. Resolving it could reshape our understanding of cosmic history, energy content, and expansion dynamics, whether through refined measurements or new theoretical breakthroughs. The outcome will undoubtedly shape the direction of cosmological science in the years to come. So is there another universe in a multiverse? The concept of the multiverse arises in several areas of modern physics, suggesting that our observable universe might be just one of many, each with its own set of physical laws or initial conditions. In quantum mechanics, the many worlds interpretation implies that every measurement creates a branching reality, with each outcome existing in a separate parallel universe. This theory preserves unitarity without the need for wave function collapse. In cosmology, inflationary theory provides another route to the multiverse idea. During inflation, quantum fluctuations cause different regions to stop inflating at different times, potentially producing bubble universes with different properties. These regions could be causally disconnected, forming a larger multiverse, with our universe being just one bubble among many. String theory offers yet another version of the multiverse. The theory's landscape of vacuum solutions suggests a staggering number of possible configurations, around 10 circumflex 500 different vacuums. Each one leads to a different universe with its own constants, particles, and dimensional structures. Some theories suggest that this vast landscape of universes could be selected through a process similar to cosmic natural selection, offering an explanation for the fine-tuning of physical constants. The anthropic principle, which is often invoked in these scenarios, suggests that complex structures like life can only exist in universes where conditions allow it. This doesn't predict specific values, but constrains the range of possible constants that would permit life to emerge. However, these multiverse models face a major challenge. They can't be directly tested. By definition, regions beyond our cosmological horizon are unobservable, and in the quantum interpretation, branching universes are causally inaccessible. This raises philosophical questions about the scientific validity of the multiverse. Still, indirect evidence and the consistency of these ideas with broader theoretical frameworks give them scientific weight. Some multiverse scenarios predict observable imprints in the cosmic microwave background, such as cold spots or anomalies caused by bubble collisions. Others suggest statistical patterns in the distribution of galaxy clusters, which could potentially provide clues. While these ideas remain speculative, the search for indirect signatures of the multiverse is an exciting frontier in cosmology. The evidence for these theories is still speculative and hotly debated. There's no conclusive proof yet, but research continues to probe for even the faintest signs. With the rise of quantum computing and advancements in information theory, new perspectives are being introduced into the discussion. Some theories propose that the multiverse could be seen as a computational system in which all quantum possibilities coexist simultaneously. Here, concepts like decoherence and entanglement play pivotal roles in determining the outcomes we actually observe. These ideas blur the distinction between physics and computation, but they still align with the core principles of quantum mechanics, further supporting the logical consistency of many worlds models. The idea of multiple parallel universes where different versions of ourselves might exist also leads to questions that extend beyond the realm of physics. It brings up deep issues surrounding identity, determinism, and the very boundaries of what we can know. From a scientific viewpoint, though, these philosophical considerations are secondary. What truly matters is whether the multiverse can provide a valid explanation for some of the biggest mysteries in cosmology and physics, like fine-tuning and unification. This is the driving force behind exploring the concept further. However, even though multiverse theories are intriguing, they are not without their challenges. One significant issue is Occam's razor, which warns against multiplying hypotheses unnecessarily. The introduction of unobservable entities into the framework raises important conceptual questions. Yet, if these models emerge organically from well-established and robust theories, they gain legitimacy. The multiverse is not a concept invented to fit data. It's a natural consequence of deeper theoretical frameworks. This makes its investigation a crucial part of our ongoing search to understand the very nature of reality. As experiments progress, the number of plausible models continues to shrink. For example, measurements of the cosmic background and its homogeneity place important constraints on how much variation can exist on a cosmic scale. Future instruments may either confirm the presence of multiverse-like patterns or rule them out entirely. For the time being, the idea remains scientifically open, though there is a lack of definitive evidence. Its status hinges on the development of new theories and the emergence of fresh data. Whether or not the multiverse is real, exploring it challenges the foundations of physics, forcing us to sharpen our definitions of explanation, prediction, and testability. This pushes scientists to construct theories that are not only logically coherent, but also firmly grounded in empirical observation. The pursuit of the multiverse drives innovation in theoretical physics and compels a re-evaluation of the role observation plays in shaping our understanding of the cosmos. In the end, the multiverse reflects the expanding range of questions that are now within reach in the field of fundamental physics. The aim is not mere speculation, but the intellectual pursuit of following the logical consequences of our best theories to their ultimate conclusions. As our theories evolve and our ability to observe the universe improves, the line between science and speculation will become sharper. If the multiverse is real, it would fundamentally alter our understanding of what the universe really means. The potential role of dark matter in explaining baryogenesis has also been explored. Some models of asymmetric dark matter suggest that the same process responsible for generating the matter-antimatter imbalance in the early universe could have also created a dark matter-antimatter asymmetry. This could help explain why the energy densities of dark matter and regular matter are so similar. These theories aim to address two major mysteries of the cosmos through a unified approach. Ongoing investigations into dark matter interactions continue to test these concepts, though no single theory has fully explained baryogenesis yet. The ongoing intersection of particle physics, cosmology, and experimental observations keeps the search alive. Each new discovery or limitation continues to refine the scope of possible explanations. The eventual breakthrough will almost certainly involve physics beyond the standard model, rooted in the unique conditions of the early universe. Understanding the origin of this matter-antimatter asymmetry is crucial for answering one of the most fundamental questions in cosmology. Why does our universe exist as it does? The imbalance between matter and antimatter is more than just a numerical puzzle. It reflects deep asymmetries in nature, encoded in fundamental physical laws. Identifying the origins of this asymmetry will help refine our models of the universe's early moments and shape our understanding of cosmic evolution. Shifting to another key question in cosmology, we also wonder how supermassive black holes, SMBHs, grew so rapidly in the early universe. These black holes, which can have masses ranging from millions to billions of times that of our Sun, are found at the centers of most galaxies. They power quasars, incredibly bright objects seen at vast distances. Remarkably, some of these quasars were already active, less than 1 billion years after the Big Bang, suggesting that SMBHs formed and grew at an astonishing rate during the early universe. This rapid growth presents a significant challenge to current theories about black hole formation. Typically, black holes grow by accreting gas or by merging with other black holes, but this process is limited by the Eddington limit, which represents the balance between gravitational pull and radiation pressure. Growing from a stellar mass seed to a billion solar mass black hole in just a few 100 million years appears unlikely under these constraints. Even continuous accretion at the Eddington limit may not be sufficient, which has spurred the search for alternative pathways for their formation. One possibility is that the seeds of these supermassive black holes were unusually massive. Instead of forming from the collapse of ordinary stars, these black holes could have formed from the direct collapse of massive gas clouds. These direct collapse black holes, DCBHs, could start with masses between 10,000 and 1 million times that of the Sun. Such black holes would require specific conditions including low metallicity, high gas inflow rates, and suppressed star formation. These conditions may have been present in the massive halos of the early universe. Another possible formation scenario involves the collapse of dense stellar clusters. In these environments, runaway mergers of massive stars could lead to the creation of intermediate mass black holes, which would then grow further through accretion and mergers. The success of this method depends on stellar dynamics and feedback mechanisms. Simulations suggest this approach could produce black hole seeds in the right mass range, though not frequently. Another formation mechanism is super-Eddington accretion, which occurs when gas is able to accrete faster than the Eddington limit without being blown away by radiation pressure. In this case, thick accretion disks and anisotropic outflows allow radiation to escape while still allowing gas to fall into the black hole. This phenomenon has been observed in some ultra-luminous X-ray sources and could also apply to early SMBHs. If sustained, this process would allow rapid mass accumulation on cosmological timescales. Mergers between black holes also play a role in their growth, especially in dense environments. Early in the universe, high rates of galaxy interactions could have facilitated black hole mergers. However, mergers alone are unlikely to account for the observed masses of supermassive black holes. They complement accretion, but accretion remains the primary growth mechanism. Gravitational wave detections from these events could provide valuable insights into the role mergers played in the formation of early SMBH. The study of high redshift quasars has informed many of our current formation models. Instruments like the James Webb Space Telescope JWST are observing galaxies and quasars at redshifts greater than 7. Their luminosities and spectra help scientists estimate the masses of black holes and the rates at which they're accreting matter. Some of these observations suggest that black holes are accreting at or near the Eddington limit, while others indicate even higher rates. These findings continue to refine our models of black hole growth and help identify potential sites for direct collapse black hole formation. As our telescopes improve in resolution and sensitivity, we can expect these conclusions to become even more precise. The chemical composition and metallicity of the surrounding gas provide additional clues about the formation environments of these black holes. DCBH models predict the presence of pristine, low metallicity gas, while stellar remnant models require more enriched regions. Spectroscopic analyses of the host galaxies provide critical evidence that helps distinguish between these formation scenarios. Some of the earliest quasars exhibit low metallicity, supporting the direct collapse theory, while others show signs of metal enrichment, suggesting a more complex evolutionary path. It's possible that both formation mechanisms contributed to the growth of SMBHs, depending on the specific conditions present. The relationship between black holes and their host galaxies also evolves over time. On a local scale, there's a clear correlation between SMBH mass and the properties of the galactic bulge, suggesting a process of coevolution. However, at high redshift, this relationship appears weaker. Some SMBHs are growing faster than their host galaxies, indicating that black hole formation may proceed independently or even decouple from galaxy formation. Understanding this process is key to explaining the structure of the universe in its early stages. Simulations such as those produced by projects like Illustris and Blue Tides play a critical role in investigating SMBH growth. These simulations model black hole formation, feedback mechanisms, and accretion processes across vast cosmological volumes. They help test different seed formation scenarios and accretion methods, revealing that multiple pathways may be necessary to fully explain the observations. These models also generate predictions that can be tested with future surveys. Radio and X-ray observations complement optical studies, providing insights into the accretion and feedback processes around black holes. High-energy emissions and jets reveal how black holes influence their environments, regulating star formation and gas dynamics. Feedback mechanisms can either suppress or stimulate galaxy growth, and in the early universe, this feedback may have been crucial in shaping the first massive structures. The origins of early SMBHs remain a complex puzzle, involving aspects of astrophysics, cosmology, and high-energy physics. No single mechanism currently accounts for all the observations, but continued observations from the JWST, next-generation telescopes, and gravitational wave detectors will help clarify the dominant growth pathways. Understanding how these giant black holes formed so rapidly will provide crucial insights into the conditions of the first billion years of the universe. The fluctuating presence of methane on Mars suggests that there could be either active sources or episodic releases from underground reservoirs. Methane breaks down quickly in Mars's atmosphere, so continuous production must be happening. However, the exact source remains unclear. Various non-biological processes could be responsible, such as serpentinization, where water interacts with olivine-rich rocks, or ultraviolet radiation interacting with carbon-containing dust. While these mechanisms don't require biological processes, they can mimic some biological signatures. To distinguish whether methane is of biological or abiotic origin, scientists need to analyze isotopic ratios, monitor the spatial distribution, and track methane levels over time. Unfortunately, the available data is sparse and often open to interpretation. Curiosity's laser spectrometer detected methane spikes up to 21 parts per billion, far higher than expected. Yet, the ExoMars Trace Gas Orbiter, which has more advanced sensitivity, failed to detect methane at those levels. This raises questions about whether methane varies spatially or over time, or if there might be calibration issues with the instruments. The gas could be trapped in small, near-surface pockets, or released in brief bursts too short for orbiters to detect. Alternatively, surface processes might degrade methane so quickly that it doesn't last long enough to disperse. Phosphine on Venus also gained attention in 2020, when a team announced its detection in the planet's upper atmosphere using millimeter-wave spectroscopy. On Earth, phosphine is mainly produced by anaerobic microorganisms, so its detection on Venus, a hot, acidic, and highly oxidizing world, was surprising. Venus doesn't have enough known abiotic sources to explain the detected levels of phosphine, which led to speculation about microbial life in its clouds. However, follow-up analyses have raised doubts about the initial findings. Some studies suggest that the spectral feature previously identified as phosphine might have been misinterpreted or caused by data processing errors. Reanalysis of the original data with better calibration tools resulted in lower or even no phosphine signals. Observations made with different instruments have also yielded conflicting results. As a result, the presence of phosphine on Venus remains uncertain. If phosphine does exist there, it could come from unknown geochemical or photochemical reactions. For example, high-temperature processes in the lower atmosphere or on the planet's surface could release phosphorus compounds, which could then rise to higher altitudes where photochemistry might convert them into phosphine. However, current models fail to reproduce the observed levels of phosphine under conditions that we consider plausible. These gaps highlight how little we understand about Venus's atmospheric chemistry. Venus's environment is extreme, with surface temperatures of around 465 degrees Celsius and pressures more than 90 times that of Earth's. The atmosphere is thick with clouds of sulfuric acid, yet at certain altitudes, temperatures and pressures are much more temperate, about 50 to 60 degrees Celsius, resembling Earth's own conditions. If life does exist, it would need to be airborne, capable of surviving in acidic conditions and adapted to limited resources. While this scenario is speculative, it isn't ruled out by current data. Upcoming missions, such as NASA's Da Vinci Plus and Veritas missions, as well as India's Shukran-1, aim to study Venus's atmosphere and surface to clarify these mysteries. Meanwhile, on Mars, the ExoMars rover and Perseverance are actively searching for signs of organics and volatile gases. Future sample return missions could offer more precise analysis of potential biosignatures. These efforts are crucial for differentiating between biological and non-biological processes. The interpretation of trace gases as potential biosignatures is tricky, though. They depend heavily on the context, environmental factors and reaction pathways on both Mars and Venus. Non-biological chemical processes still offer credible alternatives. Without supporting evidence such as complex organic molecules, isotopic anomalies, or microbial structures, claims of biological origins remain weak. For robust identification of biosignatures, we need multiple lines of converging evidence. The ongoing debates around methane and phosphine underscore the importance of cross-validation, modeling, and targeted observations. They also reflect the need to better understand the non-biological chemical pathways in planetary environments. Unusual signals could be indicative of life, but they could just as easily highlight gaps in our chemical understanding. Regardless, these findings are scientifically valuable. They don't provide definitive proof of life, but underscore the complexity of planetary atmospheres. They emphasize the need for more precise in situ measurements and a clearer framework for identifying biosignatures. Whether biological or abiotic in origin, such discoveries drive further exploration and enhance our scientific methods for assessing planetary habitability. Now let's turn to fast radio bursts, FRBs, and their possible connection to extraterrestrial life. FRBs are brief, intense flashes of radio waves originating from outside the Milky Way. Lasting only milliseconds, they release as much energy as the Sun emits in an entire day. The first FRB was detected in 2007 from archival data, and since then, hundreds of these bursts have been observed. Their high dispersion suggests they come from extragalactic sources, often from cosmological distances. The origin of these bursts is still unknown, leading to both astrophysical and speculative theories. Most FRBs are one-off events, but some repeat at irregular intervals, allowing scientists to track and localize their sources. Instruments like CHIME and ESCAP have significantly increased the detection rate of these bursts and have helped pinpoint their host galaxies. Repeating FRBs are often associated with star-forming dwarf galaxies, which suggests that their origin might be tied to young stellar populations or extremely strong magnetic fields. One strong contender for the source of FRBs is compact objects like neutron stars, magnetars, a type of neutron star with incredibly strong magnetic fields, are currently the leading natural explanation. In 2020, a galactic magnetar, SG 1935 plus 2154, emitted a burst that resembled an FRB, although much weaker. This confirmed that magnetars can produce FRB-like signals. Scientists speculate that magnetic reconnection or crustal cracking might release large bursts of energy which could occur sporadically, aligning with the observed variability of FRBs. However, not all VRBs fit neatly into the magnetar model. Some display complex time structures, show multiple components, or exhibit variations in polarization. A smaller subset of FRBs shows periodic activity, which is hard to explain with random processes alone. Some occur in environments that don't match those expected from magnetar formation. These anomalies suggest that there might be different sources or mechanisms at play. Other natural explanations include interactions between neutron stars and stellar winds, accretion processes near black holes, or even cosmic strings. Each model explains some aspects of FRBs, but struggles to account for the full range of observed phenomena. The energy scales, repetition patterns, and localization data all suggest that multiple processes or conditions may be involved. Some have speculated that FRBs could be signals from extraterrestrial technology, such as interstellar beacons or propulsion systems. These ideas, while interesting, are not based on any scientific conclusions. The brief and intense nature of FRBs could theoretically match high-power artificial emissions. However, there is no definitive evidence to support the idea that they are of technological origin. According to Occam's razor, natural explanations should be preferred unless there's solid evidence to suggest otherwise. Localization has been key in ruling out most exotic scenarios. The types of galaxies hosting these bursts, the environments in which they occur, and the redshift data all point toward a cosmological origin. No FRB has been linked to any known exoplanet systems or galactic transmitters. The dispersion and scattering profiles match what we'd expect from intergalactic plasma, further supporting the theory of a cosmological origin and excluding local artificial sources. FRBs have also proven valuable for other reasons. Even beyond the mystery of their origin, their interaction with intergalactic matter allows scientists to study the properties of the intergalactic medium. Dispersion measures help map the electron density across vast cosmic distances. FRBs are also helping to refine our models of dark matter, cosmic magnetism, and structure formation in the universe. As we continue to study them, we'll gain more insight into the universe, whether or not we solve the mystery of their origin. Advanced detection arrays and real-time processing systems are rapidly expanding the catalogue of fast radio bursts. The Hubble telescope has already discovered hundreds, allowing researchers to conduct more in-depth statistical studies. Future observatories like DSA 2000 and the SKA Square Kilometre Array will offer even higher resolution and sensitivity. These facilities are designed to detect fainter bursts, pinpoint their host galaxies, and capture counterparts across multiple wavelengths. This could provide insight into the physical conditions that generate these powerful signals. Machine learning is also playing a crucial role in classifying FRBs and identifying patterns. For instance, distinguishing between repeat bursts and one-off events, or even detecting periodicity, requires vast datasets. Automated pipelines are essential for processing this large influx of data and identifying rare events. These technologies could help uncover new subclasses or correlations, significantly increasing our understanding of the underlying mechanisms behind FRBs. The field of FRB research is evolving from initial discovery to detailed characterization. What was once a mystery is now offering valuable insights into neutron stars, galactic environments, and cosmic structures. While the exact origins of FRBs remain debated, plausible models continue to emerge. There is growing acceptance of the idea that multiple source classes exist, and ongoing observations will help refine this taxonomy. Rather than pointing to extraterrestrial intelligence, FRBs appear to be extreme but natural astrophysical phenomena. Their study is a testament to the power of curiosity-driven science, shedding light on new and unexplored aspects of the universe. As detection techniques improve, the full scope of their role in astrophysics will become clearer. Next, let's turn our attention to cosmic rays and the question of the positron excess. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that constantly bombard Earth from outer space. They cover a wide range of energies and originate from various astrophysical sources. However, Their exact origins and acceleration mechanisms are still not fully understood. Supernova remnants, pulsars, and active galactic nuclei are all suspected contributors. To pinpoint their sources, scientists need to model the acceleration and propagation of these particles across vast galactic distances. The leading theory for cosmic ray acceleration is diffusive shock acceleration, often referred to as Fermi acceleration. In this process, particles gain energy by repeatedly crossing shock fronts created by supernova explosions or jets. Turbulent magnetic fields trap and re-energize the particles, leading to power law energy spectra that match observations across multiple energy ranges. Supernova remnants have long been considered the primary candidates for the origin of galactic cosmic rays. Gamma-ray observations of these remnants support this theory. Instruments like Fermi and Hess have detected high-energy photons, suggesting that protons are being accelerated to multi-TeV energies. However, supernova may not be able to reach the highest cosmic ray energies, referred to as the Ni, which occurs around 10 circumflex 15 electron volts. To reach these higher energies, more powerful sources like pulsar wind nebulae or black hole jets may be necessary. Pulsars, rotating neutron stars with strong magnetic fields, are highly efficient particle accelerators. Their magnetospheres can accelerate both electrons and positrons to extremely high energies. Pulsar wind nebulae inject these particles into the interstellar medium, contributing to the local cosmic ray population. Pulsars like Geminga and Monogem have been suggested as potential sources of the high-energy positrons detected near Earth. Their age and distance match the energy spectrum of the observed positron excess. This excess was first noted by the Pamela, AMS-02, and Fermi missions, which found more positrons than expected at high energies. Standard models predict that the positron fraction should decrease with energy due to secondary production. The observed increase, however, suggests the presence of a primary source of positrons, whether astrophysical or exotic in nature. Pulsars provide a natural explanation for this, as they preferentially emit electron-positron pairs. Their contribution aligns well with both the energy and spatial distribution of the excess positrons. Alternative explanations have pointed to dark matter as a possible source. Certain dark matter particles, like WIMPs, weakly interacting massive particles, could annihilate or decay into positrons, producing an excess with a sharp cutoff related to the mass of the particle. However, the smoothness and lack of spectral features in the observed positron data challenge many of these models. Still, finely tuned scenarios or enhanced cross-sections might still be able to account for the observations. While there is no definitive evidence supporting a dark matter origin, the possibility is still being actively explored. Cosmic ray propagation also plays a significant role in shaping the observed spectra. Particles scatter off magnetic fields and interact with interstellar gas, losing energy and changing their composition along the way. Models like Galprop are used to simulate this transport and predict the cosmic ray fluxes we observe on Earth. However, uncertainties in diffusion coefficients, halo sizes, and energy losses complicate these predictions. These models need to be calibrated against multiple particle species, including protons, electrons, and light nuclei. Balloon and satellite experiments, such as AMS-02 mounted on the International Space Station, continuously improve our cosmic ray measurements. AMS-02, in particular, provides high-precision data on charged particles up to TeV energies. It measures the positron fraction, antiproton flux, and elemental composition, all of which help constrain both astrophysical and dark matter models. Future missions will extend the coverage and reduce systematic errors. At even higher energies, ultra-high-energy cosmic rays, UHCRs, present their own set of challenges. Their origin is thought to involve extragalactic sources, such as active galactic nuclei or gamma-ray bursts. Observatories like the Pierre Auger Observatory and Telescope Array are gathering data on UHCRs to study their arrival directions and energy spectra. While some correlations with nearby galaxies have been noted, no specific sources have been definitively identified yet. These particles might also be deflected by cosmic magnetic fields, further obscuring their origin. The composition of cosmic rays varies with energy, At lower energies, protons and helium nuclei dominate, while heavier nuclei become more prevalent at higher energies. Understanding this variation helps scientists identify the types of sources and acceleration mechanisms involved. Isotope ratios and secondary particle abundances provide additional constraints, helping refine the models of cosmic ray origins across different energy ranges. The study of cosmic rays is being enhanced through multi-messenger astronomy, where neutrino observatories like IceCube and gamma-ray telescopes provide complementary data. By detecting coincident signals, these observatories help differentiate between cosmic rays originating from transient or persistent astrophysical events. This integrated approach is offering new insights into particle acceleration and high-energy processes in the universe. As observational techniques improve, our ability to identify the exact sources of cosmic rays will become more precise. The positron excess observed in cosmic rays underscores the complexity of high-energy astrophysics. While pulsars are the leading explanation, dark matter and propagation effects remain under investigation. Resolving the sources of cosmic rays and positrons will help clarify both galactic processes and the potential for new physics. Continued data collection and modeling will be essential for advancing our understanding of this field. Finally, in 2017, astronomers detected Oumuamua, the first known interstellar object to pass through our solar system. This mysterious object has sparked a range of scientific theories about its origin and composition. The speed at which Oumuamua indicated that it wasn't gravitationally bound to the Sun, confirming its interstellar origin. Its hyperbolic trajectory showed that it had already passed its closest approach to the Sun perihelion when it was first detected. Follow-up observations uncovered even more unusual characteristics. Unlike typical comets or asteroids, Oumuamua lacked a visible coma, yet showed signs of non-gravitational acceleration, which is a behavior that couldn't be explained by gravity alone. Even more puzzling was its shape and rotation. The object's brightness fluctuated dramatically, suggesting it was elongated or flattened. Initial estimates speculated that it could have been cigar-shaped or pancake-like, with its length being at least 10 times greater than its width. Its rotation wasn't typical either, indicating it was tumbling through space. These traits were unlike anything seen in the solar system, making it difficult to classify. Scientists found it hard to explain both its shape and motion using traditional models of celestial formation. The absence of a visible tail ruled out the possibility of cometary activity, but its trajectory was still slightly altered, suggesting some force beyond gravity was at work, likely outgassing or radiation pressure. However, instruments like Spitzer found no evidence of gas or dust, even after extensive searches. To explain the acceleration, researchers proposed that Oumuamua could have been outgassing volatile ices, or perhaps was made of an unusually low-density material. Exotic ideas, such as the presence of hydrogen ice or fractal dust, were also considered. One hypothesis even suggested that Oumuamua might have been a fragment from a disrupted planetesimal. A close encounter with a star could have torn apart a larger body, forming thin, irregular debris, which could explain the object's flat shape and high reflectivity. Other theories proposed it might be a chunk of nitrogen ice from a Pluto-like exoplanet. These ideas rely on very specific initial conditions and still face significant energetic challenges. Some even speculated that Oumuamua could be an artificial object. The acceleration without a visible tail and its reflective surface led some to suggest it might be a light sail or even a probe. However, this theory remains controversial and lacks supporting evidence. While its peculiarities can be explained by natural, albeit unusual, phenomena, Oumuamua's uniqueness continues to challenge existing classifications and encourages the exploration of new possibilities. In 2019, a second interstellar visitor, 2I Borisov, was confirmed. Unlike Oumuamua, Borisov behaved like a typical comet. It displayed a clear coma and tail, along with the outgassing typically associated with comets. Spectroscopic analysis showed that it released cyanide and water, matching the composition of solar system comets. While its hyperbolic trajectory confirmed its interstellar origin, its composition seemed more familiar, suggesting that planetary formation processes might be universal. The contrast between Oumuamua and Borisov highlights the diversity of interstellar objects. While Borisov fit the known patterns of comet behavior, Oumuamua defied expectations. The small number of interstellar objects observed so far limits any broad conclusions, but future discoveries will expand our understanding. Ongoing wide-field surveys such as Pan-STARRS and the upcoming Vera Rubin Observatory are expected to find more interstellar objects, each offering a unique insight into distant planetary systems. Studying these objects provides valuable information about the processes of planet formation and planetary ejection. Both Oumuamua and Borisov were likely expelled during the early chaotic stages of planetary system evolution. Simulations have shown that gravitational interactions with large planets can expel a vast number of smaller bodies into interstellar space. These interstellar wanderers act as messengers, carrying with them clues about distant star systems. Their trajectories and compositions offer a glimpse into the conditions of other stellar neighborhoods. Spectroscopy is crucial for determining their compositions. In Borisov's case, it revealed similarities to comets from our solar system, such as dust-to-gas ratios and isotopic abundances. Unfortunately, the brief observation window for Oumuamua limited the depth of spectral analysis. However, its color and reflectivity suggest that its surface was processed by cosmic rays, possibly indicating the presence of organic-rich materials. Improved detection tools will allow scientists to track such objects earlier and capture more detailed spectra. Modeling their trajectories is another key piece of the puzzle. Both Oumuamua and Borisov entered the solar system from high galactic latitudes, with no known connection to specific stellar systems. Their paths suggest random interstellar origins, though it's challenging to track their exact origins due to gravitational disturbances. Understanding their velocity distributions may eventually link these objects to certain galactic populations or their stellar birthplace. If interstellar objects are common, they could represent a significant population passing through our solar system regularly. The likelihood of detecting these objects depends on their size, reflectivity, and trajectory. Smaller, darker objects might go unnoticed, while those that are reflective or active are easier to spot. As ongoing surveys gather more data, we'll refine our understanding of how often these objects pass through our system. In the future, missions may target interstellar objects directly. There are proposals for spacecraft capable of intercepting these objects while they are still within our observational range. Such missions could perform flybys or even return samples, allowing for unprecedented studies of materials from beyond our solar system. Analyzing these materials in the lab could provide invaluable insights into alien planetary chemistry and dynamics. Oumuamua and Borisov mark the beginning of a new era in the exploration of interstellar objects. Though they are just two examples, these objects challenge our assumptions and open exciting new research frontiers. They bridge planetary science, galactic dynamics, and astrobiology. Ongoing observation and, eventually, direct exploration will deepen our understanding of planetary systems across the galaxy. Now, let's dive into the possibility that life on Earth could have originated from space. Panspermia is the hypothesis that life, or its building blocks, originated somewhere else in the universe and was transported to Earth. This challenges the conventional idea that life arose spontaneously on Earth and suggests that microbial life or prebiotic molecules could have traveled here via comets, asteroids, or even interstellar dust. While this doesn't explain where life itself started, it proposes that life's origins could be far broader than we previously thought. The theory has gained more attention in recent years due to discoveries of life thriving in extreme environments on Earth. Microorganisms known as extremophiles have been found living in places once thought to be uninhabitable: deep sea vents, acidic springs, polar ice, and even radioactive zones. The survival of these organisms broadens the potential environments where life could persist. Some extremophiles, like tardigrades and certain types of spores, can withstand desiccation, extreme radiation, and even the vacuum of space. Experiments aboard the International Space Station have confirmed that some microbes can survive space exposure for extended periods. These findings make the possibility of interplanetary transfer of life seem more plausible. Meteorites also add weight to the panspermia hypothesis. Carbonaceous chondrites, a type of meteorite, contain amino acids, nucleobases, and other organic molecules, which are building blocks of life. These compounds could have contributed to the prebiotic chemistry on early Earth. While this isn't proof of life itself, it shows that complex chemistry could happen elsewhere in the universe. The delivery of these materials by meteorite impacts could have seeded Earth's early oceans with the necessary ingredients for life. Comets and asteroids with their icy interiors could protect embedded microbes during their journey through space, shielding them from radiation. During Earth's late heavy bombardment, our planet was hit by such bodies, possibly delivering large amounts of material. Similar processes may have also occurred on Mars, Europa, and other bodies within the solar system. If life began elsewhere, it could have spread via impacts, or variation of panspermia, called lithopanspermia, suggests that life could travel between planets on rock fragments, ejected during impacts. Martian meteorites found on Earth show that interplanetary rock transfer is possible, with some even containing structures that could protect microbes from heat and shock. This suggests that microbial life could cross between neighboring planets, potentially linking Earth and Mars in a life exchange. Directed panspermia, proposed by Francis Crick, speculates that life on Earth might have been deliberately seeded by an advanced civilization. Though this idea remains speculative and lacks evidence, it offers an intriguing perspective on life's origin and universal distribution. Critics of panspermia argue that it doesn't actually solve the origin of life problem, it just relocates it. Even if life came from space, it still had to start somewhere. However, exploring plausible transfer mechanisms and survival strategies enriches our understanding of how life might spread across the universe. Panspermia complements existing terrestrial models of life's origins and expands the scope of astrobiology into the realms of interplanetary and interstellar studies. Experiments continue to test microbial survival under extreme conditions such as re-entry heating, impact shocks, and cosmic radiation. Some microorganisms have even survived re-entry-like conditions, embedded in rock or salts, proving that life or its building blocks could indeed travel across space. These experiments help refine our understanding of the biological limits of panspermia. While no organism has managed to survive all conditions without protection, evidence suggests that survival is possible when organisms are shielded. Meteorites, interstellar dust, and comet tails carry organic molecules that can be detected using spectroscopy. Missions like Rosetta and OSIRIS-REx have examined both the surface and subsurface of celestial bodies to study prebiotic chemistry. Findings of organic molecules on Comet 67P and asteroid Bennu strengthen the idea that small celestial bodies are chemically rich. This supports the theory that organic compounds may have been delivered to early Earth. However, despite these discoveries, no direct evidence of microbial life has been found. Future missions to sample other planetary surfaces or subsurface environments such as Mars, Europa, and Enceladus are key targets in the search for life. If life or biosignatures are detected on other planets, comparing them to life on Earth will be crucial. If they share common characteristics, it could suggest a shared origin, further supporting the panspermia hypothesis. On the other hand, distinct biochemistries could point to independent origins of life. While the idea of interstellar panspermia, involving life transfer across solar systems, remains speculative, it isn't entirely impossible. The timeframes and the intense radiation exposure make it less likely, but modeling continues to explore the feasibility of such events. If debris from planetary systems were ejected, it could carry dormant microbes. If these planetary systems form in dense clusters, close encounters between them might facilitate the transfer of life. Research is ongoing to determine how often such scenarios might occur and whether they could realistically happen. Although no direct evidence for panspermia has been confirmed, it remains a scientifically plausible theory. It highlights the interconnected nature of planetary systems and the resilience of life. Investigating the mechanisms behind panspermia not only informs planetary protection protocols, but also enhances our search for life beyond Earth. Whether life on Earth originated from space or locally, panspermia broadens the scope of potential pathways for life to travel across the cosmos. Adjusting the physics of baryons is still the preferred method for reconciling the existence of early massive galaxies with the lambda CDM model. One factor to consider is the possibility of observational biases that could exaggerate the frequency of these early massive galaxies. Bright, compact galaxies are much easier to spot, while fainter or more diffuse systems can easily be overlooked. However, the prevalence and brightness of these galaxies imply that they may not be rare outliers. Surveys like Cosmos Webb and upcoming James Webb Space Telescope, JWST, projects aim to compile more statistically reliable data. As these surveys improve, we'll have a clearer idea of whether these massive early galaxies are truly uncommon or if they were more widespread. Spectroscopic data is crucial to confirming the redshifts and refining mass estimates for these galaxies. Photometric redshift data, though useful, carries significant uncertainties, especially for galaxies that are dusty or unusual in some way. Grism spectroscopy with JWST can help identify key emission and absorption lines, helping to anchor spectral energy distribution, SED models, and refining distance and mass estimates. Confirming the properties of these candidate galaxies will either support or challenge claims of rapid and extreme growth in the early universe. This is a key priority for upcoming observational cycles. The discovery of massive galaxies in the early universe fundamentally changes our understanding of cosmic history. It suggests that star formation and mass accumulation began earlier and occurred more rapidly than previously thought. Whether through revised physics involving feedback, altered cooling processes, or early halo formation, existing models must evolve to better fit these new observations. These early galaxies provide critical tests of our theories on how cosmic structure formed. As JWST and other observatories continue to expand our view of the high redshift universe, we are refining the timeline of galaxy formation. The existence of such massive systems shortly after the Big Bang is no longer a theoretical possibility. It's an empirical fact. Reconciling these findings with theoretical models is a central issue in modern cosmology and galaxy evolution. Who or what reionized the universe and when did it happen? Cosmic reionization marks a significant event in the universe's history, when the intergalactic medium, IgM, shifted from neutral to ionized hydrogen. After the universe's recombination at a redshift of Z equals sign 1100, it entered a dark age until the first luminous sources emerged. Reionization ended this period and allowed ultraviolet light to travel freely once again. Understanding the process and the agents responsible for reionization is vital for uncovering the early stages of cosmic structure. Current evidence suggests that the reionization process was more complex and extended over a longer period than previously thought. It seems to have involved multiple contributors. The primary sources of reionization are believed to be the first stars, dwarf galaxies, and quasars. Population 3 stars, with their high temperatures and masses, emitted a large number of ionizing photons. Their short lifespans and explosive deaths both enriched and transformed the surrounding environment. However, their overall contribution to reionization depends on how efficiently they formed and how widely they were distributed. Due to their short-lived and elusive nature, directly detecting these stars is challenging. Dwarf galaxies, which are more abundant, are strong candidates as reionization sources because of their ongoing star formation. These smaller systems may have emitted enough ultraviolet radiation to ionize large regions of the IgM. The difficulty lies in detecting these faint galaxies at high redshift, but JWST is beginning to uncover their population in the early universe. Their total photon output is being studied through luminosity functions and escape fractions. Quasars and active galactic nuclei also emit ionizing radiation, but their low number at redshifts greater than 6 makes them unlikely to account for the full reionization process. Their spectra primarily contribute to the reionization of helium at later times. Despite their lower frequency, they may still have dominated reionization in certain regions of space, producing patchy areas of ionization. The role of quasars in reionization is still under investigation, especially with the high redshift discoveries made recently. Several methods provide insights into the timing and progress of reionization. Measurements of the cosmic microwave background, CMB polarization, such as those from the Planck mission, give an integrated optical depth to electron scattering, suggesting that reionization was largely completed by redshift Z equals sign 6 to 7. High redshift quasar spectra also reveal absorption features, Gunn-Peterson troughs indicative of neutral hydrogen, providing additional clues about the timeline of reionization. Data from Lyman alpha emitters LAEs, which are galaxies that emit Lyman alpha radiation, help probe the state of the intergalactic medium. Their visibility is strongly influenced by the amount of neutral hydrogen surrounding them, and a decrease in observed LAE emission at higher redshifts suggests that the neutral hydrogen fraction in the IGM was increasing. Simulations of reionization model it as an inhomogeneous process. Ionized bubbles expand around early galaxies and gradually merge, ultimately ionizing the entire universe. These models are highly dependent on the properties of the sources, their clustering, and the density of the IGM. The 21 Sen fast simulation codes are used to compare these patterns with observations. Detecting the redshifted 21 Sen hydrogen signal from the epoch of reionization is a major goal of upcoming experiments, such as LOFAR, HERA, and the Future Square Kilometre Array, SKA. These radio telescopes aim to map the distribution of neutral hydrogen over time, although no definitive detection has been made yet. Escape fractions of ionizing photons, or the percentage of ultraviolet photons that escape from a galaxy to ionize the surrounding IGM, play a key role in understanding reionization. Low escape fractions mean that either high star formation rates or many smaller sources are required. Measuring escape fractions directly is difficult, particularly at high redshift, but studies at lower redshifts help to constrain plausible values. Additional constraints come from examining metal line absorbers and Lyman limit systems in quasar spectra. These features track ionization conditions in the IGM and provide valuable information about the progress of reionization. As more data becomes available, these methods will continue to improve. Reionization not only influenced galaxy evolution, but also played a major role in cosmic heating and structure formation. The feedback from photoheating suppressed star formation in smaller halos, which had a lasting impact on the mass function of galaxies and the faint end of the luminosity function. Understanding reionization effects is essential for refining models of galaxy assembly and dark matter halo occupation. While we now have a general timeline for reionization, the exact drivers and sequence of events remain open questions. Did faint galaxies dominate the process, or did more massive sources play a larger role? Was the process smooth, or did it occur in bursts? Resolving these questions requires combining observational data with advanced simulations, and upcoming instruments will provide us with sharper insights into this pivotal phase in the universe's history. The role of differential rotation and fallback accretion is currently under close scrutiny. By observing young magnetars and their surrounding environments, we may uncover vital clues about how these stars are born. Their magnetic structures also play a key role in how they emit energy and evolve over time. Interestingly, the internal magnetic field of a magnetar can be far stronger than its external dipole field. The twisted magnetic fields inside the star can actually warp the star itself, influencing gravitational wave emissions. This magnetic field decay also heats the star's crust and drives surface activity. Events such as star quakes and magnetic reconnection are thought to be the primary drivers behind magnetar bursts. These bursts not only help us study the crust's properties, but also offer a glimpse into the star's magnetic dynamics. Pulsar glitches, which are sudden jumps in the star's rotational speed, also provide crucial insights into the internal structure of these objects. These glitches are believed to result from interactions between the superfluid interior of the star and its crust. The occurrence of these glitches suggests that neutrons might form a superfluid and possibly a superconducting phase within the star. The pinning and unpinning of vortices within this superfluid regulate the transfer of angular momentum, and glitch observations offer valuable data about superfluid coupling and nuclear interactions. On Earth, heavy ion collision experiments recreate conditions similar to those found in a neutron star's crust. These experiments help to investigate nuclear symmetry energy, which plays a significant role in shaping the equation of state EOS of neutron stars. However, these experiments cannot replicate the extreme core densities of neutron stars, meaning that theoretical models must rely on extrapolating from laboratory data. As nuclear theory advances and computational methods improve, Predictions about matter behavior at supernuclear densities are becoming more refined. Future observatories are poised to enhance our understanding of neutron stars significantly. Gravitational wave detectors such as LIGO, Virgo, and CAGRA, along with upcoming missions, are expected to detect more binary mergers, providing essential data about their mass, radius, and tidal properties. X-ray missions like EXTP and Athena will measure surface hotspots and cooling rates. When combined, these observations will offer a much clearer picture of both the EOS and the evolution of magnetic fields in these fascinating objects. Moreover, understanding magnetars ties directly into the mystery of fast radio bursts, some of which may be linked to magnetar activity. For instance, the galactic magnetar SG 1935 plus 2154 emitted an FRB-like burst, strengthening this connection. If magnetars are indeed the source of these bursts, the star's magnetic field structure and its surrounding environment will play a critical role in the process. By studying how magnetars emit energy, we can gain insight into how magnetic energy is converted into powerful, coherent radio bursts. Neutron stars and magnetars serve as natural laboratories for fundamental physics, offering an opportunity to explore environments that are otherwise inaccessible here on Earth. Extreme gravity, ultra-dense matter, and intense magnetic fields. Research into these phenomena contributes to fields like nuclear theory, gravitational wave astronomy, and high-energy astrophysics. While there is still much we don't understand, ongoing observations are steadily shedding light on the complex inner workings and magnetic origins of these remarkable objects. Some researchers suggest that stripping away a star's outer envelope before collapse could allow engine power to dominate the explosion. The differences observed in these events help refine models of stellar death. Radio observations are crucial for understanding the energetics and environment of fast blue optical transients, FBOT. In the case of the cow, a significant emission of radio waves continued for weeks after the peak brightness. These radio waves trace interactions between the shock wave and the surrounding material, indicating the presence of a dense circumstellar medium, possibly resulting from mass loss prior to the explosion. Such environments influence the evolution of the light curve and the spectral features observed. X-ray data offers additional insight into the nature of the engine responsible for these events. The cow, for example, emitted persistent and variable X-rays, which suggests that the remnant is an accreting object. Its X-ray luminosity and variability far exceed that of typical pulsar wind nebulae. If the remnant is a black hole, fallback accretion could account for the energy output. Alternatively, if it's a magnetar, the rapid rotation and decay of its magnetic field could explain the observed energy emissions. Both of these possibilities are actively being studied. The frequency of FBOTs is still uncertain. They're relatively rare compared to other types of stellar explosions, like Type Ia or core collapse supernovae, but they may be under-detected due to their short duration and unusual spectra, which can make them easy to overlook. Large-scale surveys like ZTF and LSST are expected to improve detection rates. A larger sample of FBOTs is necessary to better understand their population and diversity. Theoretical models continue to evolve, with simulations exploring jet propagation, magnetar spin, and the evolution of accretion disks. However, matching light curves and spectra to specific physical parameters remains a significant challenge. FBOTs reveal gaps in our understanding of stellar collapse, the formation of remnants, and the classification of transient events. They also highlight the importance of rapid multi-wavelength follow-up observations. FBOTs like the cow demonstrate the dynamism of transient astronomy and provide insight into novel explosion mechanisms and remnant behavior. As we continue to observe, model, and classify these events, our comprehension of this emerging class of astronomical phenomena will continue to improve. These studies go beyond mere classification. They also help answer fundamental questions about how stars die and what happens to the remnants they leave behind. These deviations from standard predictions are subtle, not enough to completely challenge current models, but they do raise interesting questions about possible extensions to cosmology. Various theories have been proposed to explain the so-called axis of evil, with ideas ranging from the mundane to the more exotic. Some models suggest that anisotropic inflation, where the early universe's expansion varied by direction, could be responsible. Others propose that topological effects from a finite universe with specific boundary conditions might play a role. Even more speculative ideas involve the imprints of a multiverse or cosmic defects like textures. However, none of these hypotheses has yet been definitively supported by observations. The statistical analysis of such anomalies is complicated by what's known as the look elsewhere effect. Once an anomaly is identified, there's a risk of overestimating its significance by analyzing it post hoc. To determine how likely such anomalies are, it's essential to consider the broader expectations and the probabilities of finding similar features. Some argue that these anomalies fall within the realm of cosmic variance, while others believe that the consistent directionality across various modes makes the coincidence of these patterns highly improbable. Polarization data from the Planck satellite provides an independent way to probe these anomalies. While much attention has been focused on temperature fluctuations, polarization can either confirm or rule out directional features. So far, polarization maps have shown some alignment, though not conclusively. Future measurements may shed more light on whether these anomalies extend into polarization, which would strengthen the case for them being real cosmological features. If these anomalies turn out to be genuine, they could point to new physics beyond the lambda-cold dark matter (HESEDM) model. Possible implications include modified inflationary models, cosmic topology, or anisotropies in dark energy. These models often predict other observable signatures that could be tested by cross-checking with large-scale structure surveys and gravitational lensing. Correlations across different datasets would either support or challenge the idea that these anomalies are of a cosmological origin. Confirming large-scale anomalies is difficult due to the limited amount of independent data available. The number of large angular modes is small, which reduces the statistical power of such analyses. Cosmic variance sets a fundamental limit on the precision with which we can make these measurements. As a result, these anomalies currently reside in a gray area, somewhere between a fluke and a real physical phenomenon. Future missions will be key to resolving this. Upcoming experiments like LightBird and CMB-BSS-4 aim to provide high-fidelity polarization data, which will help refine our understanding of the cosmic microwave background, CMB, and isotropies. With improved angular resolution and sensitivity, these missions will allow us to test the axis of evil and related features, further exploring potential directional effects in the early universe. The CMB remains a cornerstone of modern cosmology, offering precise constraints on the early universe's physics. While anomalies like the axis of evil challenge the simplicity of the standard model, they could be pointing to deeper structures in the cosmos. Whether they turn out to be statistical anomalies or signs of new physics, they require careful study. As data improve and theoretical models evolve, the axis of evil will continue to provoke thought, reminding us that even the most well-understood cosmic signals may contain unforeseen complexities. The search for clarity, as always, lies at the intersection of observation and theory. Equations that describe particle interactions, electromagnetism, and gravity operate in the same way when time is reversed. This symmetry suggests that, at the microscopic level, processes can unfold in either direction. However, macroscopic phenomena undeniably exhibit a clear preference for one direction in time. This asymmetry is captured by the concept of entropy. In thermodynamics, entropy measures how many different ways a system's microscopic components can be arranged, while still maintaining the same macroscopic state. According to the second law of thermodynamics, in an isolated system, entropy will naturally increase. This increase defines the arrow of time. Systems naturally evolve from organized to disordered states, and not the other way around. For instance, a shattered glass will not spontaneously reassemble because the reverse process is statistically very unlikely. The number of possible disordered states is far greater than the number of ordered ones. Over time, entropy rises as systems settle into equilibrium. This statistical tendency explains why we experience time as always moving forward. While processes on a microscopic scale are reversible, the macroscopic irreversibility we observe emerges from this statistical tendency. The arrow of time is therefore probabilistic, not an absolute rule. It reflects initial conditions and boundary factors. The early universe had exceptionally low entropy, which enabled future increases. Why the universe began in such a low entropy state is still a mystery. This question remains a central issue in both cosmology and thermodynamics. Cosmological expansion contributes to the increase in entropy by expanding the phase space in which particles and radiation exist. As the universe grows, more configurations become available for particles and energy to occupy. Gravitational clumping, such as the formation of stars, galaxies, and black holes, also paradoxically increases entropy due to the influence of long-range forces. Black holes, for instance, represent the highest entropy that can exist for a given volume. Their entropy is proportional to their surface area rather than their volume. As shown by Bekenstein and Hawking, when matter falls into a black hole, the total entropy of the system increases. Hawking radiation introduces an additional time asymmetric effect by causing black holes to slowly evaporate, linking gravity, thermodynamics, and quantum information. In quantum mechanics, the evolution of time is governed by unitary operators, which preserve information, implying a time-symmetric process. However, quantum measurement introduces an apparent irreversibility. The collapse of the wave function selects a specific outcome, breaking time symmetry. The interpretation of this collapse, through decoherence, explains how the system interacts with its environment. Despite this, the underlying quantum dynamics remain reversible. Our psychological perception of time, our awareness of cause and effect, aligns with entropy. Memory, aging, and cognition all depend on thermodynamic processes. We can remember the past because the entropy was lower back then. Our brains process information by dissipating energy, and biological processes enforce the direction of time through irreversible metabolic functions. Some physicists propose models with bidirectional time or time-symmetric cosmologies, suggesting that time could move forward in one region of the universe and backward in another. CPT-symmetric universe models also propose time reversal could have occurred beyond the Big Bang. These ideas, while intriguing, are still speculative and lack direct empirical evidence. Nonetheless, they aim to solve the puzzle of the universe's low-entropy beginning. The arrow of time also emerges in computational systems. Irreversible operations, like erasing a bit of information, dissipate energy. Landau's principle states that deleting a single bit of information increases entropy by a fixed amount. Reversible computation tries to minimize this energy cost, but it can never eliminate it entirely. Information theory and thermodynamics are deeply connected. In everyday systems, we can observe the increase in entropy, whether it's through cooling, friction, diffusion, or chemical reactions. Even though these processes can be reversed on a microscopic scale, they appear irreversible in practice due to the overwhelming statistical probability of disorder. Microscopic order can only be maintained by supplying energy, which reinforces the one-way flow of time we experience. This irreversible flow of time results not from physical laws, but from initial conditions and statistical trends. It is a collective effect arising from countless reversible interactions that lead to the emergent irreversible behaviors we observe. Although this remains an open question in foundational physics, entropy stands as the most reliable explanation for the direction of time. Its effects influence everything from the evolution of stars to the nature of consciousness. The goal of upcoming missions is to detect thousands of both bound and unbound planets, including those with Earth-like masses. Instruments such as the UKID and JWST could also contribute through infrared imaging. Together, these missions will help clarify the size and characteristics of this population. Even without stars, some orphan planets might still retain atmospheres. Their internal heat or leftover formation energy could help maintain atmospheric dynamics. In rare cases, moons or rings may even form around these planets. If they originated from planetary systems, these objects might still carry chemical signatures from their past environments. Despite their isolation, these planets could be quite complex. Orphan planets also raise interesting astrobiological questions. Could they support subsurface oceans heated by radioactive decay or tidal forces? Without the warmth of a nearby star, their surface conditions would likely be frigid, but thick atmospheres or insulating layers might trap heat internally. While it's unlikely that these planets could harbor life on the surface, they remain intriguing candidates for exotic forms of habitability. Like stars, orphan planets move through the galaxy according to standard gravitational dynamics. They orbit the galactic center and may interact with molecular clouds over billions of years. Some may be captured by new star systems or collide with other objects. Their paths through space add complexity to our understanding of galactic evolution and mass distribution. Statistically, there may be thousands of orphan planets in the night sky that pass unnoticed. They are essentially invisible, except during rare alignment events, yet their combined mass could significantly contribute to the galactic planetary population. Studying these planets helps improve models of planetary formation, system evolution, and cosmic debris. Although detecting orphan planets is challenging, we know that they populate the dark spaces between stars. As observational tools continue to improve, we'll gain a clearer picture of their numbers and origins. Their study expands the field of planetary science beyond the boundaries of traditional star systems. Moons are common in our own solar system, with over 200 known to orbit planets. Given the vast number of exoplanets, it's reasonable to expect that exomoons are just as widespread. However, despite thousands of confirmed exoplanets, no exomoon has been definitively detected yet. Their discovery remains one of the most elusive objectives in exoplanet research. There are several reasons why exomoons are so hard to detect. They are typically smaller and much dimmer than their host planets. Their signals are subtle and often hidden by noise. The most promising detection methods include transit timing variations, TTVs, and transit duration variations, TTVs. A moon orbiting a transiting planet can cause slight shifts in the planet's position or the timing of its transit. These effects are tiny, especially for small moons. Another method involves directly detecting the moon's transit, but distinguishing this signal from noise or stellar activity is extremely challenging. High signal-to-noise ratios and multiple transits are necessary for detection. Even then, interpreting the data is complex due to various uncertainties. One of the best-known exomoon candidates is Kepler 1625 b, which was identified through TTVs and a secondary dip in its light curve. Follow-up observations with the Hubble Space Telescope provided some hints, but the evidence was inconclusive. The large size of this candidate, comparable to Neptune, raises questions about its formation and stability. To date, it remains unconfirmed, highlighting the difficulty of exomoon detection. Moons are expected to form in circumplanetary disks, much like how planets form around stars. Particularly, giant gas planets are likely to host entire moon systems. However, the efficiency of moon formation and their long-term stability depend on a variety of factors, such as planet migration, stellar tides, and orbital resonances. These dynamics can either destabilize or eject moons from their orbits, which affects both their survival and detectability. Simulations suggest that exomoons may be more common around wide-orbit gas giants, where conditions are more stable and tidal forces from the star are weaker. However, these planets are less likely to transit, which makes them harder to study. On the other hand, close-in planets are more likely to have lost their moons due to tidal stripping or collisions. This selection effect complicates the statistical analysis of exomoon prevalence. Spectroscopic techniques may also assist in the detection of exomoons. The combined spectrum of a planet and its moon might differ from the spectrum of a single planet. This discrepancy could be identified in future high-precision spectroscopic surveys. Additionally, exomoons could influence the thermal phase curves of their host planets, although these effects are subtle and would require next-generation instruments to detect. Moons can play a key role in a planet's habitability. A large moon, like Earth's, can stabilize a planet's axial tilt, which in turn helps maintain climate stability over long periods. In some cases, moons themselves might even harbor life, especially if they are tidally heated, like Europa or Enceladus. Detecting such moons would open new doors for astrobiological research. Upcoming missions will enhance our ability to detect exomoons. For example, missions like Plato and Roman will provide more precise photometry over extended periods. The JWST, with its remarkable sensitivity and resolution, could potentially detect exomoon signatures in transiting systems. Additionally, proposed missions targeting transit spectroscopy may allow scientists to analyze exomoon atmospheres. These advances provide hope that will break through the current barriers to detection. Citizen science projects like Exomoon Hunters engage the public in analyzing transit data, and their combined efforts have already led to the discovery of promising exomoon candidates. Machine learning techniques are also playing an increasing role in sifting through massive datasets, speeding up the search. The combination of human insight and algorithmic power is accelerating our understanding. As datasets grow, the chances of a serendipitous discovery increase. Confirming the existence of an exomoon requires multiple lines of evidence, including consistent TTVs, repeatable transit tips, and careful modeling. Peer review and independent reanalysis remain crucial to ensure the reliability of findings. While the field remains cautious due to previous false positives, the search continues, driven by better tools and an insatiable curiosity. Exomoons are likely to be abundant, but their small size and faint signals make them difficult to detect. Once we finally confirm their existence, they will deepen our understanding of planetary systems. Just as the discovery of exoplanets transformed astronomy, the discovery of exomoons will expand our knowledge even further. In some planetary systems, hot Jupiters may coexist with smaller inner planets, especially if migration occurred early and gently. A few systems show hot Jupiters alongside rocky, close companions, suggesting there's a wide variety of outcomes. The timing and manner of a planet's migration play a critical role in shaping its final system configuration. Transit and radial velocity surveys indicate that hot Jupiters orbit about 1% of stars similar to our Sun. These massive planets are more common around stars with higher metal content, supporting the core accretion theory for their formation. The apparent rarity of hot Jupiters may be influenced by both observational limitations and natural constraints. While their short orbital periods make them easier to detect, their actual occurrence is still relatively modest. Stellar tidal forces also have a major impact on hot Jupiter evolution. Over time, the energy dissipation caused by these tides can cause a planet's orbit to shrink or even spin the star faster. This process might eventually lead to the planet being consumed by its star. Some hot Jupiters are already spiraling toward their stars on decaying orbits, offering us valuable insights into tidal forces and planet-star interactions. The extreme conditions found on hot Jupiters are revealed through atmospheric studies. These planets can reach temperatures above 2000 Kelvin on their day side, resulting in molecular dissociation and ionization. Strong winds help redistribute heat, and phenomena like thermal inversions and clouds significantly impact their spectral characteristics. Through observations, scientists have detected substances like water vapor, sodium, and exotic materials like titanium oxide in these planets' atmospheres. These hot Jupiters serve as living laboratories for studying exoplanet climate dynamics. The magnetic interaction between hot Jupiters and their host stars may produce observable effects. Some stars with hot Jupiters exhibit enhanced chromospheric activity, and theories suggest that planet-induced star spots or flares could be at play, though solid evidence is still lacking. If these interactions are confirmed, they would offer valuable data on stellar magnetism and dynamics. Thanks to their size and brightness, hot Jupiters are prime candidates for atmospheric study. Tools like transmission and emission spectroscopy allow us to probe their composition and thermal structure, while phase curves offer insights into heat distribution and cloud formations. Future missions, such as JWST, will refine these atmospheric models and help detect even more detailed chemical signatures. Although they seem exotic, hot Jupiters provide a wealth of information about planetary physics, their migration history, dynamic interactions, and extreme environments help us understand the wide diversity of planetary systems, especially those vastly different from our solar system. By learning more about their origins, we gain a better grasp of the variety of exoplanetary phenomena that exist in our universe. Exoplanets exhibit an astonishing variety of climates, some of which are unlike anything we observe in our solar system. Some planets are so close to their stars that they've become lava worlds with surfaces so hot they glow with molten magma. Others are tidally locked, with one hemisphere constantly in daylight and the other in perpetual darkness. These unique environments lead to strange weather patterns, extreme temperatures, and unusual atmospheric chemistry. They challenge and expand our current models of planetary climates. For example, planets like 55 Cancri are classified as lava worlds, where the dayside temperatures exceed 2000 K. The rocky surfaces of these planets can melt into magma oceans that emit infrared radiation. Due to the lack of significant atmospheres, heat redistribution is limited, creating strong temperature contrasts between the day and night sides. Observations suggest complex interactions on the surface and in the atmosphere of these planets. HD1 Theta 9733b is another fascinating example, where wind speeds can reach up to 8,000 km per h. These extreme winds carry heat from the day side to the night side of the planet. The atmosphere likely contains particles of silica, which may condense and fall as glass rain, giving the planet a striking blue hue. This type of weather phenomenon has no parallel on Earth and provides unique insights into planetary atmospheres. Some hot Jupiters show atmospheric inversions, where temperature increases with altitude. This can be due to the presence of absorbers like titanium oxide or vanadium oxide. The temperature inversion depends on how much stellar radiation the planet receives and how well the atmosphere mixes. These inversions can complicate the planet's emission spectra and its overall energy balance, creating a need for sophisticated models to understand these thermal profiles. WASP-76b, one of the hottest known Jupiters, presents an extreme case with dayside temperatures exceeding 400 K. This high heat is enough to vaporize metals, and the vaporized iron may condense into metallic clouds on the cooler night side. Observations of this planet show spectral features that match this process, providing a real-time test for theories about cloud formation and atmospheric circulation in extreme environments. Tidally locked planets, where one side always faces their star, experience unique weather patterns. The constant heating of the substellar point drives vertical convection, and the cooling of the night side creates temperature gradients and pressure differences. These conditions can generate jet streams and vortices that impact the global climate. Understanding how heat is redistributed on these planets is crucial for modeling their habitability and weather dynamics. Some exoplanets may have photochemical hazes in their atmospheres, similar to those on Titan. These hazes can affect the planet's albedo reflectivity, influence how the atmosphere escapes into space, and affect overall climate stability. Ultraviolet radiation from the star drives chemical reactions in the atmosphere, which leads to the formation of aerosols that absorb and scatter light, distorting the planet's spectrum. These hazes pose challenges for interpreting observational data. Extreme eccentricity in a planet's orbit can create further complexity. For planets like HD 80606b, the highly elliptical orbit leads to drastic changes in the amount of radiation they receive from their star. These changes can trigger shocks in the atmosphere, causing transient weather events and rapid temperature spikes of hundreds of degrees. Studying these transitions offers insight into the atmosphere's response and its thermal inertia. Exoplanets orbiting red dwarf stars face intense stellar flares, emitting ultraviolet and X-ray radiation that can strip away their atmospheres or drive atmospheric escape processes. Repeated flaring could disrupt the climate stability of these planets, though strong magnetic fields or thick atmospheres could provide protection from this erosion. These planets serve as crucial tests for our understanding of atmospheric retention and magnetic shielding in exoplanetary systems. High gravity on massive planets also affects their atmosphere. These planets compress their atmospheres, altering circulation patterns and increasing convection efficiency. Cloud formation occurs at higher pressures and temperatures, and these effects must be accounted for in global climate simulations that aim to model exoplanetary environments. Albedo and reflectivity vary greatly among exoplanets. Some hot Jupiters have atmospheres that absorb most of the light they receive, making them appear nearly black, while others reflect much of the light due to clouds or hazes. Albedo plays a significant role in thermal balance and surface conditions, and understanding a planet's reflectivity helps astronomers infer its atmospheric composition and cloud structures. Each extreme climate among these exoplanets adds a new piece to the puzzle of planetary science. Whether it's vaporized metals or shockwave heating, these planets push the boundaries of what we know about atmospheres. They offer crucial insights into how planets and their climates function under extreme conditions, and they help refine our models of planetary formation and climate dynamics. Through continued observation, we can better understand the limits of planetary environments. Jupiter's auroras are far more than brief flashes of light. They are continuous and multifaceted. These stunning polar lights consist of three main features: the main oval, satellite footprints, and polar emissions. The main oval surrounds the pole, driven by co-rotation enforcement currents. Footprints appear as bright spots created by individual moons like Io, Europa, and Ganymede. Meanwhile, polar emissions are more chaotic, influenced by variations in solar wind. X-ray observations have shown that Jupiter's auroras follow a pulsating pattern. Chandra and XMM Newton telescopes have detected bursts of energy every few minutes, likely due to magnetospheric reconnection events or wave-particle interactions. Additionally, ultraviolet data from Hubble shows corresponding changes in auroral brightness, offering clues about magnetic field dynamics and plasma behavior. Magneto-hydrodynamic waves also play a significant role in these auroras. These waves, which involve oscillations in both the magnetic field and plasma, propagate along field lines, accelerating electrons toward the planet's atmosphere. Upon colliding with atmospheric molecules, they create the auroral glow. This interaction helps explain certain patterns in emission timing and spatial distribution, which differ from the solar wind-driven auroras on Earth. Solar wind does still influence Jupiter's auroras, but its impact is less pronounced. During periods of high solar activity, the magnetosphere gets compressed and energized, boosting polar emissions and sometimes triggering transient auroral features. This dual influence, both internal and external, makes Jupiter's auroras unique. Observing these lights is like studying a natural laboratory for magnetospheric physics. Jupiter's moon Ganymede, which is the only moon with its own magnetic field, adds an interesting twist to the system. Ganymede's mini-magnetosphere interacts with Jupiter's magnetic field, producing distinct auroral patterns. These include double auroral ovals and changing footprints, allowing researchers to study how planetary and satellite magnetospheres interact. These features provide insight into how multipolar magnetic environments operate. NASA's Juno mission has delivered incredibly detailed data from Jupiter's auroral regions. With its ultraviolet spectrometer and magnetometer, Juno measures the strength of Jupiter's magnetic field and monitors particle precipitation. Its orbits across magnetic field lines allow for direct sampling of the source regions, confirming the presence of powerful currents in areas where particles are accelerated. These findings help refine and validate theoretical models of magnetospheric activity. Auroral activity on Jupiter also varies with factors like latitude, local time, and magnetic anomalies. Some regions show persistent hotspots or enhanced emissions, potentially linked to deeper atmospheric flows or variations in the planet's internal magnetic field. By mapping these features, scientists are linking Jupiter's auroras to its interior structure and overall atmospheric circulation, a fascinating area of ongoing research. Jupiter's auroras are not just visually spectacular, they provide vital information about the complex interplay between magnetism, plasma, and planetary rotation. By studying them, we can deepen our understanding of not just Jupiter, but also exoplanet magnetospheres, which may exhibit similar auroral phenomena. These lights are a window into planetary behavior, offering keys to the planet's internal and external energy systems, bridging planetary science, astrophysics, and space plasma dynamics. Saturn's rings are among the most recognizable features in our solar system, composed mostly of water ice with traces of rock and dust. Their bright, reflective nature suggests they are relatively young, possibly only 100 to 200 million years old. This challenges earlier ideas that the rings have existed since Saturn's formation. Data from NASA's Cassini mission has provided new insights, showing both clues about the rings' origin and signs of ongoing erosion. Cassini's gravity measurements revealed that the ring's mass is smaller than expected, suggesting they may be more vulnerable to external forces like meteoroid bombardment. Over time, contaminants accumulate, which would darken the rings. The fact that the rings remain bright indicates that either they are young or that they are frequently replenished. The relatively pure water ice in the A and B rings further supports the idea of a recent formation. If the rings were primordial, they would likely be much darker and more eroded by now. One possible explanation for the rings' youth is that they were formed relatively recently, potentially by the destruction of a moon that ventured too close to Saturn. Tidal forces inside the Roche limit could tear an icy moon apart, spreading debris into orbit that gradually evolved into the current ring system. The existence of moons both inside and near the rings supports this theory, as some moons help shape the edges of the rings. Despite their beauty, Saturn's rings are slowly disappearing. Cassini observed a phenomenon known as ring rain, where particles from the rings spiral into Saturn's atmosphere due to electromagnetic forces. This process is gradually depleting the rings, and estimates suggest they could be gone in 100 to 300 million years. This means we are living in a relatively brief window where the rings are visible in their current state. The D ring and parts of the C ring are decaying the fastest. Various forces, including charged particle interactions, micrometeorite impacts, and plasma drag, all contribute to this erosion. Saturn's powerful magnetic field accelerates the process. The rate of loss varies across the rings, but the overall trend points to gradual fading. Alternative theories suggest that the rings could be older and are regularly replenished by collisions between small moons, but maintaining their purity under constant bombardment is challenging. Cassini's data supports the idea of a younger, more transient system, but seasonal changes also affect ring visibility and structure. As Saturn orbits the Sun, the angle of solar radiation changes, influencing ring temperature and photochemistry. Long-term observations show subtle changes in the ring's opacity and particle behavior, which help scientists model their evolution. Saturn's rings are not uniform. They contain gaps, spokes, density waves, and temporary clumps. These features arise from resonances with Saturn's moons and self-gravity. Analyzing these structures provides insights into the mass distribution and particle interactions within the rings. This research also helps inform models of disk dynamics, which can be applied to systems around young stars. Although other planets such as Jupiter, Uranus, and Neptune have rings, none match the scale and brilliance of Saturn's. Saturn's rings remain an extraordinary and dynamic feature. Their apparent youth and ongoing decay raise questions about long-term stability, making this a fascinating area of study. Whether due to chance or cosmic timing, Saturn's rings offer a rare glimpse into gravitational and collisional processes at work, and as we continue to analyze the data, their story of origin and eventual fate becomes clearer. For now, they stand as one of the most captivating features of the outer solar system. Uranus stands out in the solar system with an axial tilt of about 98 degrees, effectively rotating on its side compared to the other planets. This unique feature sets it apart and continues to intrigue. Scientists, understanding why Uranus has such a tilt is a subject of ongoing study, offering valuable insights into planetary dynamics and the early history of our solar system. Uranus stands out in the solar system for its extreme tilt of about 98 degrees, meaning it essentially rotates on its side compared to most other planets. This unusual axial tilt causes its poles to point toward the Sun alternately throughout its 84-year orbit, resulting in extreme seasonal changes. The tilt impacts everything from its seasons to the behavior of its magnetosphere. To explain how Uranus ended up in this position, scientists speculate it experienced a massive collision early in the solar system's history. The most widely accepted hypothesis suggests that Uranus was struck by a large protoplanetary body, which knocked it into its current orientation. Simulations support the idea that a single giant impact could produce such a tilt without destroying the planet. This collision likely occurred after Uranus had mostly formed. Another possibility is that multiple smaller impacts over time could have gradually shifted the planet's axis, which would suggest a more chaotic and extended early history for the planet. Each collision would contribute a small change to the planet's angular momentum, and these models fit with our understanding of early crowded planetary systems. However, directly testing these ideas is challenging. Looking at Uranus's moons can provide more clues. Their orbits align with the planet's equator rather than the ecliptic, suggesting that the whole system was reoriented together. A gentle tilt would allow the moons to remain in stable orbits. But if the tilt were caused by a violent event, it could disrupt or even reaccrete the moons. Some models propose that Uranus's current moons were formed after the planet was tilted, while others suggest that the planet's disk was warped but not destroyed by the impact. The planet's internal structure could also hold traces of this cosmic collision. A layered interior with distinct compositional gradients could have been created by the energy released during the impact. The mass and speed of the impactor would determine how much mixing occurred within the planet. Simulations show that Uranus could have retained some thermal anomalies as a result, which could explain why it has an unusually low heat output compared to other planets. Uranus's magnetic field is another intriguing aspect. Unlike Earth's field, which is relatively centered, Uranus's magnetic field is tilted and offset from the planet's center. This odd configuration might be the result of disruptions in Uranus's internal convection, likely caused by the giant impact. However, modeling this magnetic structure remains difficult without better data. The extreme axial tilt leads to unique seasonal effects on Uranus. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness, creating dramatic atmospheric changes. This unusual seasonality helps explain some of the planet's atmospheric dynamics. While atmospheric observations of Uranus are still incomplete, comparisons with Neptune, a similarly sized ice giant with a more typical axial tilt, highlight Uranus's peculiarity. Neptune likely avoided the catastrophic impact that caused Uranus's tilt, or had a different early history. These differences help refine models of planetary evolution and their dynamical histories. Uranus's tilt also has important implications for exoplanet studies. Many exoplanets could undergo similar shifts in orientation due to massive collisions or gravitational interactions. Directly observing axial tilts on distant planets is difficult, but the tilt of a planet strongly affects its climate and habitability. Uranus provides a nearby example of how such events can impact a planet's long-term evolution. Future space missions may provide further insight into Uranus's tilt, offering valuable lessons for planetary scientists. Uranus was only visited once by Voyager 2 in 1986, and a dedicated orbiter could reveal much more about its interior, magnetosphere, and moons. Detailed gravity measurements could shed light on the planet's core structure, while atmospheric probes could test thermodynamic models. These findings would be essential for validating the various theories about how Uranus became tilted and help scientists understand the broader processes of solar system formation. Understanding Uranus's tilt also contributes to our overall knowledge of solar system formation. It demonstrates the unpredictable nature of planetary outcomes. Small differences in initial conditions can lead to vastly different planetary histories. Uranus is not just tilted. Its orientation tells the story of ancient cosmic collisions and planetary violence, preserved in its axial inertia and orbital geometry. The full explanation for Uranus's tilt remains partially solved, but more research is needed to piece together the whole story. Earth's rotation, like Uranus's, is not fixed. The length of a day gradually changes over time due to complex interactions within Earth's atmosphere, oceans, solid core, and mantle. Recently, scientists observed that Earth is spinning slightly faster, shortening the length of a day by a few milliseconds. These fluctuations are caused by a combination of geophysical and astronomical processes. The redistribution of mass across Earth's surface is one major contributor. Seasonal melting and freezing of glaciers, for example, shift water between land and ocean, which affects Earth's moment of inertia and alters its rotation speed. When mass moves closer to the planet's rotation axis, Earth spins faster, much like a figure skater pulling in their arms. Conversely, when mass moves outward, the planet slows down a bit. Ocean currents and atmospheric winds also affect Earth's spin. Stronger winds near the equator, for instance, can transfer angular momentum to Earth, speeding up its rotation. Phenomena like El Niño and La Niña cycles along with global pressure systems, influence wind patterns, which in turn affect the length of a day. These changes are tracked with precision using satellite data. Another factor influencing Earth's rotation is the interaction between the outer core and the mantle. The outer core rotates slightly differently than the mantle, and electromagnetic coupling and friction at the boundary lead to angular momentum exchanges. This core-mantle interaction affects Earth's spin over longer time periods. Seismic data and measurements of Earth's magnetic field help scientists model these effects. Post-glacial rebound also contributes to changes in Earth's rotation. As ice sheets melt, the crust gradually rises, redistributing mass and subtly changing Earth's shape and rotation. This ongoing response to the last ice age affects the planet's rotation over centuries. Tectonic activity and earthquakes can also cause small abrupt shifts in Earth's mass distribution, slightly altering the rotation period. For instance, the 2004 Sumatra-Andaman earthquake shortened the day by about 2.7 microseconds. Though these changes are tiny, they highlight how sensitive Earth's rotation is to mass redistribution. Human activity has a smaller but measurable effect on Earth's rotation. The construction of reservoirs, groundwater extraction, and deforestation all alter the distribution of mass. While these anthropogenic changes are minor compared to natural processes, they are still detectable. The cumulative impact of human-induced changes on Earth's spin is an area of ongoing research. Satellites that measure gravity are crucial for tracking these fluctuations in Earth's rotation. In recent years, Earth has set records for the shortest days ever measured since atomic timekeeping began. These anomalies are still being studied, with hypotheses suggesting possible causes such as core acceleration or global climatic shifts. As geophysical models improve and long-term data sets grow, we will have a better understanding of these strange variations in Earth's spin. If Earth continues to speed up, scientists may eventually need to add a negative leap second to keep atomic time aligned with Earth's rotation, a fascinating challenge for timekeeping. Timekeeping is vital for everything, from navigation to scientific research, and recent changes in Earth's spin have raised some eyebrows. Although Earth's rotation fluctuates slightly over time, the recent trend of it spinning slightly faster is something new. While these fluctuations don't pose a risk to everyday life, they do have implications for systems that depend on precise timekeeping, such as satellites and navigation systems. These changes in Earth's rotation aren't just a curiosity, they give us valuable information about the planet's internal dynamics. Earth's rotation is influenced by complex interactions between its surface, atmosphere, oceans, and core. Even small shifts in any of these systems can slightly alter the spin rate. For example, seasonal changes like glacier melting and freezing affect the distribution of water on Earth, shifting mass between land and oceans. When mass moves closer to the planet's axis of rotation, Earth spins faster, much like a figure skater speeding up by pulling in their arms. On the other hand, when mass moves away from the axis, the rotation slows down. Ocean currents and atmospheric winds also play a role in these fluctuations. Strong winds near the equator can transfer angular momentum to the planet's solid core, speeding up its rotation. El Niño and La Niña cycles, along with pressure systems, can change global wind patterns, which influence the length of the day. While these changes are small, they accumulate over time and are closely monitored by satellite data. Another contributing factor to changes in Earth's rotation is the coupling between the outer core and the mantle. The outer core rotates slightly differently than the mantle, and this friction creates a transfer of angular momentum. This interaction can affect the spin rate over long periods. Earth's rotation is also influenced by post-glacial rebound, where the crust rises slowly as ice sheets melt, redistributing mass and subtly changing the planet's shape and rotation. Tectonic activity and earthquakes cause small, abrupt shifts in Earth's mass, slightly affecting its rotation as well. For example, the 2004 Sumatra-Andaman earthquake shortened the length of the day by 2.7 microseconds. Though these shifts are tiny, they show how sensitive Earth's rotation is to changes in mass distribution. Human activity also impacts Earth's rotation. The construction of reservoirs, groundwater extraction, and deforestation all alter the mass distribution. albeit on a smaller scale than natural factors. These human-induced changes are still measurable, and their cumulative effects are actively studied. Satellites that track gravity help monitor these fluctuations with high precision. In fact, in 2020 and 2021, Earth set records for the shortest days measured since atomic timekeeping began. Scientists are investigating whether this could be due to core acceleration or other climatic shifts. As we continue to refine geophysical models and collect long-term data, we'll gain a clearer understanding of these variations. If Earth continues to speed up, we may eventually need to introduce a negative leap second to keep time synchronized. Space debris or orbital junk is becoming an increasingly significant concern as more satellites and spacecraft are launched. Made up of defunct satellites, rocket fragments, paint flecks, and other remnants from decades of space activity, there are now more than 36,000 objects larger than 10 centimeters in orbit, with millions of smaller pieces scattered around Earth. These fragments travel at incredible speeds and pose a serious risk to satellites and space stations. The density of debris in space has reached a point where collision risks are becoming a major concern, especially in low Earth orbit. This region is particularly crowded, and the danger of cascading collisions known as the Kessler syndrome could make certain orbits unusable. Once one satellite breaks apart, its debris could trigger more collisions, creating an ever-growing problem. Even small fragments, when moving at orbital speeds, carry significant kinetic energy, making them a long-term hazard for spacecraft, space stations, and future missions. The primary sources of debris include accidental explosions, satellite malfunctions, and deliberate anti-satellite tests, such as those conducted by China in 2007 and Russia in 2021. Collisions, like the one between Iridium and Cosmos satellites in 2009, further contribute to the debris problem. Without intervention, space could become increasingly unsustainable, making space debris management a top priority. Efforts to reduce debris include strategies like passivation, which involves venting residual fuel from satellites to prevent explosions. Many new satellites are also being designed with deorbiting plans, ensuring they burn up in Earth's atmosphere at the end of their mission. Regulatory frameworks, such as the 25-year rule for orbital disposal, aim to limit long-term clutter. However, enforcement is inconsistent, especially among private operators and older missions. One promising approach is active debris removal, which is still in development. Concepts include using harpoons, nets, robotic arms, and lasers to capture or redirect debris. The European Space Agency's Clear Space One mission is testing a claw-like mechanism to capture debris. Other methods involve using ion drives or tethers to lower objects' orbits. While progress is being made, technical, legal, and economic challenges remain. Tracking and collision avoidance have improved thanks to radar and optical systems that monitor known objects. Conjunction alerts allow spacecraft to maneuver to avoid collisions, but predicting smaller or untracked debris remains difficult. The growing number of satellites, especially from mega constellations like SpaceX's Starlink, is making congestion worse. These large constellations will add tens of thousands of satellites to space in the coming years. Although many of these satellites are designed with deorbiting plans, the sheer volume presents challenges for managing space traffic. The persistence of orbital debris depends on the altitude of the objects. In low Earth orbit, atmospheric drag eventually causes debris to re-enter the atmosphere. In high orbits, like geostationary orbit, debris can remain for centuries. This long lifespan means that today's actions will have consequences for the future accessibility of space. Sustainability in space requires forward-thinking design, responsible mission planning, and global cooperation. The International Space Station already performs regular avoidance maneuvers to protect itself from debris. However, small fragments have already caused minor damage to modules and solar panels, and future missions face increased risks. The growing uncertainty about debris-related threats has raised insurance costs for satellites, further emphasizing the need for proactive measures. The legal framework for space debris is lagging behind the rapidly advancing technology. The Outer Space Treaty prohibits ownership of celestial bodies, but it lacks clear enforcement when it comes to debris generation. The issue of liability for collisions remains unclear, making it urgent to establish international norms for debris mitigation and removal. Transparency and data sharing are crucial, and public awareness of space debris is growing, with media coverage and educational campaigns helping to highlight the problem. The long-term viability of space for research, exploration, communication, and defense depends on responsible stewardship. Preventing a space debris crisis is a shared global responsibility. While space is not yet ruined, its accessibility could be compromised if current trends continue. Without coordinated action, the accumulation of debris could hinder progress in space exploration and commercial ventures. Earth has been struck by catastrophic impacts in the past, from the mass extinction event at the Chicxulub crater to smaller airbursts, reminding us that planetary defense against near-Earth objects, NEOs, is critical. Thousands of NEOs are tracked, and while most pose no threat, some have orbits with a non-negligible collision probability. Preventing an impact requires a range of strategies, and the earlier a threat is detected, the more options are available. The most developed method for deflecting an asteroid is kinetic impact. This involves sending a spacecraft to collide with the asteroid at high speed, slightly altering its trajectory. NASA's DART mission successfully demonstrated this technique in 2022 by impacting the moonlet Dimorphos, reducing its orbital period around its parent asteroid. This experiment confirmed that momentum can be transferred from the spacecraft to the asteroid, marking a significant step forward in planetary defense. Kinetic impactor methods work best for small to medium-sized asteroids, especially if they are detected years in advance. A small change in velocity can prevent a future collision if applied early. However, this method's effectiveness depends on the asteroid's structure and composition. For example, rubble pile asteroids may absorb momentum inefficiently, making deflection more challenging. Another approach is using gravity tractors. This involves placing a spacecraft near the asteroid for an extended period, where its gravitational pull slowly shifts the asteroid off course. This method is precise and gentle, but requires a long lead time and significant fuel for the spacecraft. Alternatively, focused solar energy could be used to deflect an asteroid by concentrating sunlight onto its surface, causing material to vaporize and push the asteroid off course. This technique, although slow and requiring precise targeting, could be a viable option for smaller objects. In extreme cases, nuclear options might be considered. A standoff nuclear explosion could deliver a powerful push to alter the asteroid's trajectory, while subsurface detonations might vaporize part of the asteroid, pushing it off course. However, these methods come with political, legal, and technical complications, as well as the risk of fragmenting the asteroid into multiple hazardous pieces. Efforts to track and predict the orbits of potentially hazardous asteroids are ongoing, with missions like Pan-STARRS and the upcoming NEO Surveyor mission working to catalogue these objects. Space-based infrared telescopes are particularly useful for detecting dark asteroids, and once these objects are identified, orbital modeling can predict their future positions with increasing accuracy. Space debris is becoming an increasingly serious concern as more satellites and rockets crowd Earth's orbit. This orbital junk, which includes defunct satellites, rocket fragments, and paint flecks, is moving at high speeds and poses significant risks to active spacecraft. Currently, there are over 36,000 tracked objects larger than 10 centimeters in orbit, and millions of smaller fragments that could potentially damage or destroy satellites. As the amount of debris grows, so do the risks of collisions, especially in low Earth orbit (LEO), which is already heavily congested. One of the greatest threats in space is a phenomenon called the Kessler syndrome, where a single collision between two objects creates a cascade of debris, triggering more collisions and making certain orbits unusable. Even tiny fragments can be dangerous, because they carry immense kinetic energy. The result could be a long-term hazard for satellites, space stations, and future missions. This risk continues to increase, making the need for debris mitigation a top priority. Most of the debris originates from accidental explosions, rocket stage failures, and intentional actions like anti-satellite tests. These activities, such as China's 2007 test and Russia's 2021 destruction of a satellite, have created thousands of dangerous fragments. Collisions, like the 2009 Iridium Cosmos satellite event, add to the problem. If left unchecked, space could become an unsustainable environment for future space exploration and commercial activities. To address this, efforts are underway to reduce debris. One approach is passivation, where satellites are designed to vent out their remaining fuel to avoid explosions at the end of their life. New satellites are also being equipped with deorbit plans to burn up in Earth's atmosphere when their mission ends. Some guidelines, like the 25-year rule for orbital disposal, aim to limit the time debris stays in orbit, but enforcement is inconsistent, especially with the rise of private companies in space. A promising solution is active debris removal. Technologies like harpoons, robotic arms, and lasers are being tested to capture or redirect debris. The European Space Agency's Clear Space One mission is using a claw-like mechanism to capture debris as part of a larger effort to clean up space. Other techniques involve using ion drives or tethers to lower debris into Earth's atmosphere, where it will burn up. However, there are still technical, legal, and economic hurdles to overcome before these methods can be widely implemented. While tracking and avoiding collisions has improved with the help of ground-based radar and optical systems, predicting the movement of small, untracked debris remains a challenge. The growing number of satellites, especially large constellations like SpaceX's Starlink, only increases the problem. In the coming years, tens of thousands of new satellites will be launched, making it essential to find a way to manage space traffic effectively. International cooperation is crucial, but it remains limited. Debris in low Earth orbit will eventually fall back to Earth due to atmospheric drag, but objects in higher orbits, like geostationary orbits, can remain in space for centuries. This means that today's actions could affect the accessibility of space in the future. For space to remain usable for scientific, communication, and defense purposes, we need forward-thinking design and responsible mission planning. The International Space Station already performs avoidance maneuvers to protect itself from debris, and small fragments have already caused minor damage to its modules and solar panels. Future missions without proper mitigation face higher risks, and insurance costs for satellites are already rising due to debris-related threats. The legal framework around space debris is also lagging. The Outer Space Treaty prohibits ownership of celestial bodies, but does not address debris generation or set strict enforcement mechanisms. Liability for collisions remains unclear, making the creation of international guidelines for debris management and removal essential. Transparency and data sharing will be key in improving space debris management, and growing public interest, driven by media coverage and educational campaigns, is helping to raise awareness of the issue. The long-term sustainability of space depends on global cooperation and stewardship. Preventing a space debris crisis is now a shared responsibility. While space is not yet ruined, its accessibility is at risk. Without coordinated action, the accumulation of debris could severely hinder scientific research, space exploration, and commercial ventures. Proactive measures are necessary to preserve space for future generations. As we continue to explore the universe, we must also prepare for the existential risks posed by near-Earth objects, NEOs. Earth has experienced catastrophic impacts before, from the asteroid that caused the extinction of the dinosaurs to smaller but still significant airbursts. These events underscore the need for planetary defense systems to protect against NEOs, some of which have orbits that pose a real collision threat to Earth. To prevent a potential impact, scientists are developing a range of mitigation strategies. The earlier an NEO threat is detected, the more options we have to address it. The most well-established method for deflecting an asteroid is kinetic impact. This involves sending a spacecraft to collide with the asteroid at high speed, altering its trajectory just enough to prevent a collision with Earth. NASA's DART mission successfully demonstrated this technique in 2022 by impacting the moonlet Dimorphos, which confirmed that momentum could be transferred from a spacecraft to an asteroid, effectively changing its orbit. Kinetic impact is most effective when the asteroid is detected years in advance and is of a small to medium size. A tiny change in velocity, even as small as a few millimeters per second, can divert an asteroid from a collision course with Earth. However, the success of this method depends on the composition and structure of the asteroid. Rubble pile asteroids, for example, may absorb momentum less efficiently, making it harder to deflect them. Another proposed method is the gravity tractor technique. This involves positioning a spacecraft near the asteroid and using its gravitational pull to gently change the asteroid's trajectory over time. While precise and effective, it requires long lead times, fuel, and advanced guidance systems. A third concept is focused solar energy. By using mirrors or lasers to concentrate sunlight on the asteroid's surface, we can vaporize material, creating a small but continuous push that gradually alters its path. As a last resort, nuclear options are also considered. A nuclear explosion, either at a safe distance or below the asteroid's surface, could push the asteroid off course. However, these methods carry significant risks, including the potential for the asteroid to break apart into smaller, still hazardous pieces. Political and legal complications also come with the use of nuclear devices in space. Efforts to detect potentially hazardous asteroids are already underway, with surveys like Pan-STARRS and the upcoming NEO-Surveyor mission working to catalogue these objects. Space-based infrared telescopes, in particular, are crucial for spotting dark asteroids, and once an object is identified, orbital modeling can predict its future path with increasing accuracy.